an echo. You just do it. Turn out okay. Okay, I heard an echo.
No, I think it's
not. You just do it. Turn out okay.
Okay, can you mute Landon? Can you mute Landon?
Just do it. Turn out okay. Alright, sorry about that.
I think it's feedback from Landon, yeah. Sorry about
that. Once again, you just do it, turn out okay. Even if someone's playing the background music. Oopsie. So how are you all doing today?
I'm doing well.
Doing okay. Although I do have like I don't know what it is, but my throat is a bit affected by something, and that's why my voice is a bit rough today. But so I'm doing mostly fine. Yeah.
So you two celebrating the holidays at all?
No, I'm actually out right now.
Oh.
I need to go and get some afterward. But it's probably going to be very busy.
Yeah, holidays usually are. Yeah, we don't have any stores here. It just got legalized a few months ago, so they're still building stuff.
Yep.
Oh, yes. How about you, Landon? You celebrate the holidays today?
Well, there's always holidays to celebrate and other fun things that are happening in our favorite universe. So, sure.
Yeah, Landon had to celebrate that holiday 420 later today.
Well, there's a number of things that happened today in history. So, but good morning, good afternoon, or good evening.
But today we're
time zone and latitude.
Today we're going to talk about a little bit earlier than most history stuff teaches. Way earlier.
Yes. Although this time we're speeding up the show even more. Instead of talking about 100 million years, we're actually talking about several billion years this time.
Yep.
So, I hope folks are doing well.
Yeah. But if you don't remember what we talked about last time, here's a recap for y'all.
Yes.
Okay. And so if you remember in BE0, we talked about the Big Bang process. In BE1, we talked about really the first second of the Big Bang process. In BE2, we covered the first sort of 100 million years. And we entered what is known as the Dark Ages. This is not the misnomered term that sometimes people apply to history of civilization, but rather a true age of the universe. When we left off, the universe went dark. There wasn't really anything creating new electromagnetic radiation to speak of. I mean, there was, but not much.
And one thing to note is that previously we had to use a logarithmic time scale because the events that occurred in the first few seconds were on a scale so small we had to use a logarithmic scale to blow them up, basically. But now we are moving to a time period when things were moving a bit slowly, so now we can use a linear time scale.
And so you see that BE3 there on this slide is rather short, but if you go to the next slide, hint, there we go. We now have a much better thing. And so we are actually in ages where we have some reasonable amounts of direct observation, and we certainly have, although certainly our mysteries there. One of the things that the James Webb Space Telescope, that's the JWST, is doing is giving us a lot more information about this the early part of this scale. Like I said, BE 1 and BE2 only covered less than 1% of the history of the Big Bang process.
Yeah, so we're starting today. Also, we're starting around 100 million years. We're kind of starting, I guess, when the Dark Ages ended, and
Right.
but what happened sort of during the Dark Ages?
Well, certainly the universe continued to expand. The visual part of the universe continued to expand. The temperature continued to drop, and things began in this process. Now, how long it occurred is something that is not well understood, but there was some period of time before the first stars actually began to emit light. So we went from the Big Bang flash, which occurred around 378,000 years after the Big Bang process started. That's when the photons, when the universe cooled to the point where you no longer had plasma. Those free protons grabbed free electrons and formed neutral hydrogen. And so the cosmic background radiation that we see are the photons that were in the early radiation-dominated universe going free. But at that stage, we didn't have presumably material that was dense enough to actually form stars. Now, as to when the first stars formed in their nature is something which is under active research. We do know that at this stage, at 100 million years, the universe is also roughly neutral. That is, most of the protons and electrons found each other, and the gas was roughly neutral in charge.
I think also one thing to note is that during the Dark Ages, from the Big Bang flash, when the universe was still, even after the Big Bang flash, the universe was pretty hot, 4,000 Kelvin, give or take. And then it cooled to around 60 Kelvin after 100 million years or so. And 60 Kelvin, I don't know how much it is in Fahrenheit, but it's like minus
minus
200 and minus 210 degrees Celsius, right?
Yeah.
About
But certainly the density of the universe went way down as the physical universe expanded.
Yeah. And back then, when the universe was 4,000, like right after the Big Bang flash, it was 4,000 degrees, so the universe was still like a very bright orange. But then, as it cooled down, the universe became very dark, as it is today. The background is just black.
Yeah. I mean, in this particular situation, the visual universe expanded by a factor of 55 over this period of 100 million years. So we're starting at the stage where it is hypothesized that there were no, there's no active stellar fusion going on. There were no stars, but again, I think maybe going to the next.
One last thing to note here is that, like, as you say, that there was no active star fusion during this time, but we do have one important source of photons, and that is the 21 centimeter radio waves emitted by neutral hydrogen, and that will become very important later.
Yeah. So
was that a good station to listen to back then? Those radio waves? Was that an AM or FM station?
Next slide. So we're going to be the next probably very important point. We'll talk about other things in this thing, but one of the things that occurred in this time period, we'd say 200 million years to 1 billion years. It could be actually even earlier than 200 million years, and really depends upon the first stars, is called reionization, where the first stars that switched on sent out very energetic light, ultraviolet light, which reionized, stripped electrons from their protons or their nuclei, and reionized the universe.
Why is it called reionization? It's a bit of a bit of a softball question, but I think it's also important to clarify why we call it reionization, because
Let's go on to the next slide.
Yeah, exactly. Because in the early universe, everything was ionized before, but now it's becoming, like during the Dark Ages, it was neutral, but now it becomes reionized again.
Yeah,
and it's why it's
And so, in this period of time of the second ionization, if you will, of the universe, where this first stars come, this process, we continue to cool. We go from 60 Kelvin down to 19 Kelvin, and the redshift continues to expand in this particular situation. So the universe is going to go from redshift of 6, from 20 to 6. So the universe is going to expand by almost 3 1/3. The visual universe is going to expand by almost 3 1/3. And so the visible universe is going to go from about 600 million light years, about 1.6 billion light years.
Yeah, still pretty tiny compared to the universe today. Like it went from 0.7% of the current size, and then after 1 billion years, it is 2% of the current size of the observable universe.
Yeah.
Well, it's still only 1 billion years old, or 9 billion years old. You're still a baby. The universe is still a baby now.
Yes.
Well, but the reionization occurred probably before then. In fact, it may have occurred as early as 150 million years after this area. This is one of the things, the active areas, that James Webb Space Telescope is trying to give us some insight on of these first stars.
Mm-hmm. Reionization has like an interval, where it's a point where it first started, and then a point where it's pretty much completed, because the whole universe, as you can see in the image on the top right, the universe reionized in bubbles, basically bubbles that surround the first stars and the first galaxies. That's how it reionized.
It was a process, and again, it wasn't instantaneous. When it took the light, particularly the ultraviolet light from the first stars, it took the speed of light for that thing to begin to ionize the material beyond the stars, and so it's a process that occurred over a particular period of time. Now, if you look at the size of the original universe when we were around 100 million years in, we were somewhere around 600 million light years across visualized. So that means that the first stars, light would take the first stars at least 600 million years to go across that process. So it wasn't an instantaneous thing. But the cosmic dawn is probably a better way of saying than reionization. Because reionization sounds like the universe went instantaneously ionized again. It really was the beginning of the cosmic dawn. And such that is there. By the way, there's a rustling and
for Vandalia, we can hear rustling from your mic.
Sorry.
Question about reionization. So reionization happened as a consequence of light being emitted from the first stars. Mm-hmm. So it's the end of the Dark Ages, and that light reionizes things. What are the consequences of that from the perspective of how the universe is evolving? Do you now have a more or less opaque universe? Does it cause shock waves or bunching up or sort of density perturbations? Does it make it easier or harder for matter to accrete, or is there any influence of that at all? Do we have any idea?
Well, we have some. There's active area research, but certainly, as you said, the stars when they switch on, when they ignite, when they flash, will push matter out, and so those were the very beginnings of the shock waves that were not induced as sound waves in the very early universe, right? Before the dominant sound structures, the dominant motion of matter came from the early universe, and for that, go back to like our BE1 episode for some of those types of things. So yes, they begin to have motion, large scale motion. Obviously, the collapse of the stars was also motion. And if we're lucky, we'll be able to see gas clouds in the process of collapsing and heating up even before the first stars show up. But we'll get to later when we talk about galactic formation. So yes, another thing that happens, of course, is when you have ionization. Now some things become more opaque than others. And so there's some difficulty in photons no longer are now hitting plasma and are not giving us a clear.
Is that what's happening in this picture? It being opaque and stuff.
And although the universe is also expanding and cooling, so the other process is it's thinning out, right?
Yeah, but it's not as opaque as it was before the Big Bang flash. Certainly,
Yes.
certainly.
That's a matter of density. Yeah. So as a general rule that people should keep in mind, plasmas tend to be more opaque than neutral gases. Because they are free charges, and a photon can hit a free charge and scatter off of it and bounce. And so actually, Vandalia, I think in a certain sense, it might make more sense to imagine that you get this flash, and then as it reionizes, it turns this sort of area around the star into a plasma. And that actually might make it would make it, I think, more opaque. But the universe doesn't become opaque again at a macro level because it's expanded so much and it has started clumping down into things. So it's extremely dilute.
And we're talking about not a temperature induced plasma from the universe being hot. We're talking about plasma because there's ionizing radiation that's stripping electrons off of what it was otherwise would be neutral atoms. But the opaqueness, I mean, stars are not transparent because they're plasma, right? You can't see through them in normal light for that reason. So we
right
started
now,
that cosmic dawn.
Sorry.
Right? There's a cosmic dawn is starting from the first stars. But also the first stars are somewhat unusual, perhaps not the type of stars. They have some usual properties, but in addition, we're talking about the motion, because the question was asked about the motion of material in the bubbles. The other thing that's likely to happen is some of these first stars formed were extremely massive and exploded in supernovae. So some of the shock waves that came out were probably less due to the stars switching on and more impacted by massive stars dying. We'll talk about it in a little bit. I'm sorry, you were saying?
Oh, who was that?
Yes, yeah.
Sorry. I was thinking about right now today. Most of the universe is re-ionized, so pretty much any lone atom in the vacuum of space is an ion, basically, almost always, except for things like inside grains of dust, perhaps, right?
Well, molecular clouds certainly have lots of neutral atoms. But
really?
But there are plenty of ions out there being created by stellar processes.
All right.
Are molecules even a thing yet, or are we still atomics?
Yes.
Yes.
Yes. Sorry.
But it's only when the heavier elements were made. Like maybe right now you do have a hydrogen gas, right? H2 perhaps,
Yes.
right?
Well, I mean, remember that the Big Bang process, nucleosynthesis, Big Bang, gave us about 74% hydrogen, about 25% helium, and a small fraction of what became lithium after it decayed. That was essentially. There might have been traces of other things, but that was essentially it. And in the cosmic dawn, when the stars first turned on, that's all we had. So those first stars were hydrogen, a little bit of some helium and traces of lithium. When the first stars went supernovae, then we started seeding more material. So if you talk about chemical bonds, if you're just talking about the era where we just had mostly hydrogen and helium, there wasn't really anything useful because helium doesn't really play well chemistry wise with other material. You could get neutral hydrogen, so you get H2, but it wasn't until a little bit after the cosmic dawn, when the very first stars that were massive went supernovae, that you started getting heavier elements scattered in the clouds. But we should probably go to the next excellent slide.
I just did.
Okay, so the what is known as the Song of Hydrogen. It is when it's nearby at around 1420 megahertz.
So is that
21 centimeter band? I'm sorry.
So is that country, rock, jazz, blues?
It's kind of a hum, if you will. It's a glow.
It's AM for sure.
And it's also a case where it's an area of the spectrum that's reserved for astronomy, because this is a fairly important thing. Until of course they started showing that Doppler shift is there, but for something which is co-moving with you, that has hydrogen, you will get this problem of as you see of the you can get situations where the electron that's orbiting the proton and hydrogen can flip, and the flip results in this 21 centimeter wavelength or 1420 megahertz.
Yes, and it's also like they both, when it flips, it can emit or absorb this photon at this particular wavelength.
Yes.
Yeah. So that's one thing I found, is that like when the first stars ignited and it started to heat up the surrounding hydrogen gas, that's when the hydrogen atoms began to absorb more of this 21 centimeter photons than it emits. So this could be detected as a dip in the CMB spectrum.
Yeah.
Why does it go that way? Why is it a dip?
I don't know why. I don't know. I found it. Yeah.
Well, I mean, one of the things is that if the hydrogen is absorbing these photons, doing the reverse, right? We think about things, but if the absorption of a photon causes a flip, then essentially the resulting energy is absorbing the microwave. What was then 21 centimeter, right? When the universe was dominated, had lots of 21 centimeter photons. Those can be absorbed by hydrogen. So when radio astronomers look out in the universe, one of the things they look for is this song of hydrogen Doppler shifted, and it can come in several forms. It can come in emission of clouds where the electrons flipping, or it can come in absorption of clouds absorbing that radiation, because it's a symmetric process.
Okay.
And probably go on to the next one here. So if we look at this stuff now, obviously it's Doppler shifted, so it's no longer 21 centimeters. It really is the song of hydrogen in its form. Because remember that in this process of reionization, we have a redshift going from 20 to 6, meaning that the photons that we're looking at have been expanded by a factor of 20 to about a factor of 6 in this process. So in this graph here, what we see is the frequency of things, and you can see how it changes in brightness. Now remember the redshift as you're going from left to right is showing from 160 down to about 6, and you can see where in the dark ages things began to form, and then you get the cosmic dawn. In this case, it looks like it's around with redshift around 150 million years. If you see the top, you go from 10 million years to about 1 billion years. So around 150 million years or so, the first stars form.
Yeah.
Things began to heat up. Things began to ionize. You have radiation that is causing the electrons to flip around.
It might also begin when the curve starts to dip downwards around like 100 million years. Yes.
Yeah.
Also that.
And again, this is general, right? We're talking about general. It's not instantaneous. There's a gradual process of there. Now this particular graph and these researchers have an interpretation about galaxy versus star formation, but just from the data, we know that we have a dip in brightness as the first stars start forming, and then as the light from those first stars start going out, it begins to reionize, and you get an increase in brightness before it kind of ends as things thin out.
And that's the red part of the top graph when you have an increase in the amount of 21 centimeter photons. That have been redshifted, of course, since then. Yeah. You can clearly see an increase, and that's when the gas become reionized. Yeah, it's a very intuitive figure. Yeah.
And I say on this chart, the thing that Richard and Liam add as speculation is the word first galaxies form. That's speculative. What we do know is during the Dark Ages, when the universe went basically quiet electromagnetic wise in terms of new radiation being emitted, at some point we began to get heating, and we began to get some of the first stars forming. And the light from the first stars starts impacting larger and larger volumes of space. Again, it's not an instantaneous thing; it's a process, and so before the first stars actually ignite, with fusion, they were collapsing, and so there was a heating going on, and leading up to that. The question of what and how is an active area of research, but we do know that stuff started heating. And then the light from the first stars started shining and ionizing things. And presumably those first stars went supernova, so they had other bangs going on.
So we don't have a very clear idea about the timeline of galaxy formation.
Yes.
That's something that's definitely still an active area of research. And the sort of, which came first, the star or the galaxy, maybe an ill-posed question. We have things that are collapsing, though. I mean, at some point, obviously, we have stars. Were the first things that collapsed, do we think that those first things that sort of collapsed became stars? Or is there a possibility that some of it may have collapsed directly into a black hole, and then accretion around the black hole could have started some ionization?
I've seen that too. Yeah,
and those are all areas of active research. These are processes that are there. I suspect the answer is going to be a synthesis of galactic formation, galactic cluster formation, black hole formation, neutron star formation, and stars switching on. I think we had a whole process of things there. But as far as what's dominating here, we don't know. What we do know is that after the Dark Ages, the universe began to heat up in chunks, not as a whole. Remember, as a whole, the universe is cooling down, but chunks began to heat up. So when we talk about heating begins, what Pritchard and Liam should have said was there are local areas of heat developing, not that the universe was heating up. The universe is still cooling down from about 20 Kelvin down to about 6 Kelvin, but there were localized areas of densification and localized areas of heating before stars and galaxies and dwarf galaxies and black holes and neutron stars and other things are forming in some combination of stuff.
Yeah, for the longest time, I always wondered, you know how in the center of our galaxy is at least proposed to be a black hole?
It is. There is a black hole in the
near
the center of our galaxy.
I always wondered if that black hole was
the
remnant of one of the very first stars.
We don't know. I mean, but there are processes, and part of it is part of the things you're getting from LIGO is trying to investigate the sizes of black holes. But we're getting a little bit off the track here.
I think it's also the issue is also that like stars have a very distinct significant effect on the photon speed. But of course, whether something is a galaxy or not, that when you talk about that, you cannot really see it in the photons. You have to use something like the JWS telescope to actually see the formation of the first galaxies, right? So that's the only way to observe whether galaxies were there or not. Yeah.
In terms of the difficulty of observing this era is in part because things have so redshifted, right? That the frequencies have been shifted down from a factor. You see a factor of 40 to 20 and so forth. That means that if you have a star begin to shine and its visible light has been stretched way down into the infrared and even in the microwave, and depending on how far you're stretching the photons. Also, the fact that it is so far away, it's going to be dim. Also, the fact that there's so much stuff. If you look about things far away, there's so much stuff between here and there that stuff gets absorbed, and so the result is it's difficult to observe in the area. You have to have, for example, telescopes that are very cold, because even the thermal temperature of the telescope itself will shine and blind you in the areas of frequencies you want to look at.
That's why the JSW, the James Webb Space Telescope, is always facing away from the sun.
Yeah, and again, I don't mean to have to disrespect Pritchard and Liam in this diagram. I would not have written first galaxies form. I would not have, because that's an assumption. I would have said, localized heating or regions of localized regions began to heat, right? Not that the universe is heating up. The universe is definitely cooling down. The reionization process starts somewhere in the redshift of 20 to 15. Presumably that's because stars are doing this. And so somewhere between 150 million years and 250 million years, the reionization gets quite widespread. The reionization ends, or I would say reionization process ends, because the universe is now expanded in quite a bit. And so it's you no longer have a dominant reionization process. I mean, from the point where reionization begins to end, the visible universe doubles in size and temperature drops. But localized areas begin to heat up, and in fact, you also have in this process supernovae occurring. somewhere around if the reionization is beginning just beyond 20, maybe at 18, there's also between 18 and 15 supernovae occurring, and they're going to do another bit of thing to the surrounding gas.
I would guess that the supernovae causes the curve to bend upward again. Like you see that the heating begins, that is when the curve goes down, and perhaps when you have like a very violent, energetic things occur, maybe I'm speculating right now, of course, but
No,
maybe that's why it goes upwards. Yeah.
Well, I think what they're saying is, I think what they should have said was heating of localized density, pockets. Whether those things are dwarf galaxies, whether they're protostars, is to be determined. But there's localized heating of certain regions that begin, and that tends to diminish the brightness of the song of hydrogen. And again, it's not 21 centimeters; it's 21 centimeters multiplied by the redshift. So,
yes,
so the actual frequency you're going to see is there. So, in that sense, when you look out, the radio astronomers have to look at a wide range of frequencies from 2.1 meters down to 21 centimeters would go from 1 to 100 in that. Is that right?
2.1 2.1 meters is 10 times 21 centimeters.
Yes, I did that incorrect. I should say 21 meters would be 1,000 times. So 2.1 meters would be 21 meters is equal to 21 centimeters would be right. 100
centimeters are the worst. Everywhere else, we're really good about only doing with every third power of 10, but with centimeters, it's 2.
Yeah, so 0.21 meters, the 0.21 meter song of hydrogen at 2.1 meters would be 10 on the scale, and at 21 meters would be 100 on the scale. So you're going from about 21 meters down to about 1 meter, right? And so those are the wavelengths in radio telescopes you have to look at, or microwave.
At redshift to 21 centimeters would become 4.2 meters.
Yeah,
I believe.
How far down do our radio telescopes go?
They can go quite low. The problem is, how effective can you be? As you get longer wavelengths, you need to have different types of dishes. I mean, the dish versus frequency size is important, but there's different technologies to pick up very low wavelength material. The problem is, Earth is quite noisy in low frequency stuff as well. So the question becomes, how effective are you at listening? So let's move on to the next one. I think would be the
Lyman.
The Lyman Alpha Forest. And Sophie, who wants to talk about this?
Mm-hmm.
Yeah. So to understand what the Lyman Alpha Forest is, I think you want to know what the Lyman transition is. And so in hydrogen, in atomic neutral hydrogen, the transition from the ground state of that atom to the first excited state is called a Lyman alpha transition, and it is characterized by an energy of approximately 13.6 times 75% electron volts, according to the Balmer series. And what that means is that if you have an atom that then decays from the excited state down to its ground state, it will release a photon. And that photon that it releases will have a wavelength of 121 nanometers.
0.75.
0.57.
0.57.
Yes.
Right.
And this is a very difficult thing to sort of detect and use It's not a convenient part of the spectrum,
No.
but it's a high enough energy photon that it can ionize a lot of things generally. And for instance, it has well more than enough energy to knock another electron off of another thing that isn't already in its ground state. So you get a lot of these photons being emitted because hydrogen, when you make it go, when its electrons go up and down, every time the electron falls down, it's going to emit some of these. So they emit in this very particular sort of wavelength. And then as that light travels out, the universe is expanding and the light gets redshifted as it goes.
Now, as I say, if this is happening nearby, there's no redshift. We're dealing with things that are in the ultraviolet, right? You would not be able to visibly see this. But as it redshifts, it goes down. And in fact, what you can see, if you, what this is talking about in that figure, you see the person, they are observing, probably not looking with their eyeballs, but observing some energetic event far away.
Which produces a lot of photons of all sorts of different frequencies.
Yeah, even gamma radiation. Yeah.
Some of these might be, we're talking about here the Lyman alpha emissions of, let's say, gas soaring around an energetic event. They'll start off as ultraviolet, and as the universe, as you get expansion in the universe, the wavelengths drop. They drop from ultraviolet down into the violet, visible, and on into the red and beyond. So what this diagram is showing is that there's these clouds of stuff that can reabsorb those hydrogen alpha photons.
Yeah.
And the result is that you see dips in the spectrum where those gases are absorbing. You're not seeing the actual gas, you're seeing the effect of the gas absorbing those photons. And the result, when you look at the spectrum, you'll see these dips, and the dips correspond to gas clouds between you and the other object.
And I believe only neutral hydrogen does this. Like if you have ionized gas, it won't have this effect on the spectrum. But when the light passes through neutral pockets of hydrogen, that's when you get these dips.
Yeah, I mean other gases can do this, but yes, it's primarily a neutral hydrogen that is giving you this particular material. And the material also is going to be relatively cold, so it itself is not really glowing much in this area at all. But it gives you, when you look at, let's say, a distant quasar, and there is surrounding that quasar hydrogen, which is called where you have the decay of a excited state down to ground state. You could begin to trace gas clouds between you and the quasar by looking at dips in the absorption from those.
Yeah, and those dips will correspond to, for example, when that light, which was originally emitted at 121 nanometers, that light will redshift, and when it gets 4 times more redshifted, suddenly it is now resonant with a different transition in hydrogen, and it gets absorbed. So you're not seeing the light be absorbed in that case, what I just described. It's originally emitted as 121 nanometers. Then later it will be absorbed by different sort of transitions. You can also have light that is generated by a very hot source that maybe it starts out at 50 nanometers. And it just goes through hydrogen because it's not at the right wavelength to be absorbed by it. And then eventually it's going through, it's living its life and passing through the universe. And at some point it redshifts and it's on resonance with this line. And
let's go to the next page, the next slide, by the way.
Yeah.
Talk about this.
Yes. And if it happens to pass through a cloud of hydrogen at that time, you'll see this dip. And then it finishes passing through that cloud, and it keeps going on. And then some of the other light moves on resonance, and it allows you to map out along your line of sight where these clouds of matter were. Because first you get a dip here, and then you get a dip here, which means that there was a chunk of light that when it went through that first cloud was absorbed. And then later, 100 million years later, it went through the second cloud. Different light gets absorbed by the same effect, though, because of the redshift.
Yeah. So in this thing, we're seeing wavelength going from left to right. And the term forest is all those little spikes. It's like people describe it as a forest of little spikes or dips, depending on which side you're going on.
Yeah. And all of these things, it all requires the fact that you're only going to get absorption when the energy of the photon is matched precisely with the energy difference between energy levels in whatever atom you're talking about.
Yeah. But it's a very important way that astronomers can map the material, which is not necessarily even visible as a star, and it's a very important part of studying our cosmos. So I think we could go on to the next item, which is stellar evolution.
What do you say next?
Never mind. I was just maybe thinking about something about the previous slide, but we can move on.
Yeah. So we're going to talk about stellar evolution. Let's go on to the next slide as well. So
the Stellariferous era.
Yeah, I mean, and stars formed after the Dark Ages, and the Dark Ages are ending when those first stars began to form. Some of those stars last a short amount of time. Some can last extraordinarily long amount of time. And the era is going to be, quite long. While there are certainly stars forming now, the some of the life of those stars is varies very much on material. So let's go to the next one as well in terms of what are stars. Our sun is a star.
Really?
And in fact, sometimes when people talk about the nearest star, sometimes forget the sun. Now that notion of the sun being a star was actually a radical idea. Giordano Bruno, who was burned at the stake for heresy, one of the heresies that Giordano Bruno suggested was that our sun and these dots in the sky called stars are the same thing. He actually was one of the first people to publish dramatically a statement of that effect.
Yeah, I don't know if we have a troll or something in chat. Apparently we have a craziness in chat, I think.
Well, it's fine. If they want to do that sort of thing, I would, unless they're spamming, let them
not yet
learn. I wouldn't call them a troll unless
a troll. I meant I don't know if they're a fake creationist or a real one.
That's sometimes hard to tell. Some creationists are really grifters. Others have a true belief in creations. You don't know. So yeah, let the person, unless they're spamming, I would suggest letting them be.
I believe in the time, maybe not in the time of Bruno, but before then, we've thought of the fixed stars as stars, and anything that moved across the sky were wandering stars, like the moon,
yes,
the sun, and also the planets.
Yeah,
like they were
called points of light. Yeah.
But
good.
But people have been measuring with astonishing, impressive precision where the stars have been in the sky for thousands of years, and it turns out that we have records from around 2,000 years ago of exactly where Polaris was, for instance. And Polaris was not called the North Star back then because it wasn't up there. So actually, everything in the sky moves on some time scale,
but for different
different reasons. For different reasons, the motion of Polaris is not due to actually like it moving. It's due to the Earth's tilt changing over 26,000 year cycle.
But let's go back to stars, right? So stars come in all types of shapes and sizes and colors. That's what this diagram is showing you. You will see
you cannot
in
even
the
see the
center.
sun.
If you look at very carefully in the center, you'll see the sun, which is sort of average star of average size. Now, what this is really focusing on is some of the bigger stars that are around, and there are. But you see, these are sort of supposed to be sort of scaled stars. Some of my favorite stars are some of the larger ones. As there's an expression by an Australian referring to stars as tubby stars, and we can see some of the tubby stars, the big ones there. Certainly, my favorites are Eta Carina, A and B is one of the items there. Antares is another favorite star of mine. It has a very different style of stuff. And variables such as Polaris are also there. So there are lots of really interesting stars in this process that are showing. So probably could go to the next one.
Okay.
So what are stars? Gravitationally bound blobs of matter whose temperature and pressure is enough to sustain fusion. Now there are things like planets, which include exoplanets, that are not massive enough to have pressures to cause fusion, but somewhere between planets and stars are this boundary line of what they call brown dwarfs, where there might be some fusion going on in the core, but it's kind of smoldering. It's kind of like a smoldering ember. And that's...
Uh-oh. Oh, there he is. You got cut off for a second. So, yeah. You were explaining brown dwarfs. So re-explain brown dwarfs.
Okay, so when objects get to about 13 to about 80 times the mass of Jupiter, they may have enough internal temperature and pressure to sustain fusion. It may not be very active fusion. It may be more smoldering like an ember. But brown dwarfs are the lower mass boundary between when it's a planet and when it's begun to be a star. Going on to beyond things that we know, beyond about 80 times Jupiter's mass are things where fusion is the dominant process.
Question: do we have any observations directly of brown dwarfs?
Yes, and there are certainly M-class stars and so forth, and L-class stars are certainly there. Yes, we do have observations. They tend to be, as we've developed infrared telescopes and infrared technology, we have a much better sense of it. But yes, we definitely have direct observations of these low mass stars. So next.
I think also one thing to note is that it says that the fusion is what prevents further gravitational collapse. So when the star contracts to the gravity, eventually.
Let's go on to the next. Yeah, the next thing.
Yeah, yes, eventually fusion becomes enough to balance the force of gravity. Yes.
So the surface of the star is where the event goes from translucent to transparent. So inside the surface of the star, the plasma creates this translucency, but the internal core where fusion is going on pushes outward, whereas gravity wants to crush it inwards. And so as you get farther away from the center of mass, the gravitational interaction gets weaker and weaker. At some point, it gets weak enough that essentially the material can escape by radiation pressure. And that's considered sort of the boundary of the star. Now, stars with more mass have more fuel, and more fuel causes the star to sort of change its behavior. So those brown dwarfs have relatively little mass from a point of view of being a fusor, and they will then sort of smolder for a very, 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 very long time. Whereas stars have lots of mass, have lots of pressure, and have a very different fate. Let's go on to the next one.
All right.
So as I say, the size is there. The brown dwarf probably starts around 13 times the mass of Jupiter. So the planet Jupiter is not sufficient to turn into a star, and you'd have to find another 12 Jupiters and pile it in, and even then you'd have difficulty in getting fusion to start. So Jupiter's not a failed star; it just never got to the point even close to becoming a star. But at some point, as you add more mass, you get to a point of average stars like our sun. But what's going on inside the core that's causing it to counterbalance the gravitational collapse? Let's go on to the next one.
All right. So real fast, I think it's talking about already. How did all these hydrogens or heliums all tend to get together to form the star?
By gravitational collapse and shockwaves.
Yeah. You need to have some density perturbation in order for it to collapse. If you have a just perfectly uniform like universe with mass, there's no like local area that's denser than any other that then like attracts more stuff. And so that's how shock waves really speed things up, because suddenly they create a pressure wave, and you now have overdense areas that can become more and more overdense and more, and they heat up, and they also radiate some of that heat away, which is why they don't just go down and then like bounce. And then eventually you get enough, and gravity is squishing it hard enough that you will start to get nuclear reactions, like we can see in this image here.
Yeah. So yes. So this hydrogen to helium fusion is one of the common processes that we see in cores of stars. Most stars are dominated by this hydrogen helium fusion process, and it really is kind of in several stages. Remember, the primordial hydrogen came from the Big Bang nucleosynthesis. Refer back to BE1 and that first second, or beyond the first second when you got nucleons forming, so BE2. What happens is a sort of several stage process. First of all, two hydrogen nuclei fuse together and form deuterium. They'll kick out an electron, they'll kick out an antineutrino. I believe it's an antineutrino that gets its form there, if I may.
I think it would kick out a positron, right? Because it has
positron.
Yeah,
well, that's
so
right.
Then it probably is a regular neutrino if it's a positron.
That's right. It's going from positive. No, it's going from positive to neutral. It's going to be losing a positive charge.
Yeah, which means it's kicking out a positron.
By kicking out a positron, yes.
It's also kicking out a neutrino. The V. The V is a neutrino,
yes,
right?
That's right.
Yeah.
Yes. It also has gamma as well.
Yes.
And
That's the second step for the creation of helium.
well, there's gamma.
You'll have it in
gamma.
the first step too.
Yeah, the first step as well. And in the process, the next one is deuterium and hydrogen forming to form helium-3.
Is it next slide or just same slide?
No, this
Same
is
slide.
in this one. In this one here, we're still here. I should point out that there are also some now in earthbound stuff, like such fusion reactors, we tend to use trying to fuse helium and tritium. Stars have a different density and containment thing than, let's say, fusion reactors, and so they can perform some of these more difficult transitions, of which we see here. So you'll get deuterium and helium fusing to form helium-3, and helium-3 can fuse together to form helium-4 with more hydrogen. Of course, there's gamma coming off of there, as well as when you have the transition. Whenever you have a transition of a neutron proton neutron type of thing, then you'll get also some neutrinos being kicked out as well.
And this process is called the proton-proton chain, like a particular type of fusion chain reaction, right?
Yes.
That's
yes.
And I found this this is the most dominant type of fusion that occurs in fairly low mass stars, like 1.5 and lower times the mass of the sun, basically.
Now there's always this kind of fusion going on in even higher mass stars, but they tend to be dominated by more energetic stuff that we'll talk about a little bit later. There's another process that goes on. Go to the next slide.
Right.
And this should have said CNO cycle rather than HTE fusion. And it has to do with a circular process of carbon, nitrogen, oxygen, nitrogen cycle, right? And hydrogen is being fed in, and you get gamma rays and other neutrinos and other particles coming, positrons being kicked out in this process. It was something that while it's not as dominant as the hydrogen helium fusion that goes on the core of the sun, is going on the core of the sun. Now, the very first stars that didn't have much carbon, nitrogen, oxygen weren't doing this. This catalytic cycle occurs in more mature stars.
It's the, like I found this that the previous reaction, the proton chain, this is more energetic at lower temperature compared to the CNO cycle. But when you increase the temperature even further, eventually the CNO cycle becomes more energetic than the proton-proton chain.
Well, in some ways, you have, in the more energetic stars, you actually have abundance of carbon, nitrogen, oxygen in there. This CNO cycle is going on our sun as well. It's just not as dominant. All right, next.
All right.
I have a question about this really quick.
Okay.
How prevalent is the theft of catalytic converters in stars?
Well, catalytic converters. Well, I should say stars tend to be very light in their amount of platinum that they have. Also, people who might try to faking recycling platinum inside stars by trying to cut the platinum out, find it very difficult to go inside stars and come back out.
Okay.
Can the circle get bigger, or is that this established circle?
This is a fairly established dominant.
I did find that there are like different versions of the CNO cycle. Like some cycles use the fluorine as well. some cycles. Yeah.
I don't know if we have other. Well, we'll see other cycles going on.
Yeah.
But this is the dominant CNO cycle, and it's called CNO cycle because it's carbon, nitrogen, oxygen cycle. Next.
All right.
So while stars have fusion going on their cores, the stuff that's not part of it, most of the volume of a normal star is not a fusion core, but has a material around it. And it depends upon the type, the mass of stars as to what's happening. So in the middle one, the yellow one here, with masses around the mass of our sun, you have essentially radiative stuff coming out of the core, hot radiative core, and there's an outer envelope which is being heated and undergoing convection. So the hotter material rises to the surface, and the cool material sinks down into these convection cells. So on our sun, you have internal fusing radiative zone surrounded by convection. In low mass stars like brown dwarfs and things that there tend to be a brown half.
Also red dwarfs as well, I think, right? Red dwarfs too.
The stars themselves are primarily convection. There's not much going on in their cores. So low mass brown dwarf stars have very little fusion going on inside, sort of smoldering, and the predominant volume of those stars are convection. But something odd happens when you go the other way, when you get about 1.5 times the mass of the star. What's happening is that you all of a sudden invert, and instead you have convection around the fusing core and radiation from that convection going out even further. It's an odd process, but very massive stars are almost entirely convection in their volume.
I found some answers that cite the CNO cycle, because in larger stars, the CNO cycle is very energetic, and that causes a very steep energy gradient. And because of the steep energy gradient, you have convection because of the steep energy gradient.
The CNO cycle is a fixed amount of energy as atoms go through the cycle. The issue is, in a star, how much material is undergoing CNO cycles. In massive stars that have more larger nuclei, particularly plenty of carbon, the CNO cycle will be much more dominant. Where the stars have exhausted most of their hydrogen in their core, they're not going to be very energetic in the hydrogen fusion. It'll be a shell around the outside. So the CNO cycle is a fixed amount of energy. The question is what's going on in the star. So let's go back to let's go to the next one.
All right.
So we'll talk about main sequence stars, but the astronomers have these classes of stars, and you see in this chart going from top to bottom O, B, A, M, F, G, M, and L is even, and there's other things. L is even colder beyond that set. But you see the temperature goes from very high, plus 30,000 Celsius, down to much more mundane stuff. In fact, in the brown dwarfs, we've detected brown dwarfs whose surface temperature is around 300 Kelvin, relatively mundane temperatures, right? They can go from high to low. The stars that are higher temperature tend to be bluer. That their light is sort of is dominated in the blue end of the spectrum, whereas low mass stars tend to be red to infrared. Now, the size as well will change, right? Because higher temperature stars are a result of more energetic processes going on, usually in the core, and so they'll be bigger as well.
And the sun is a G class star, right?
Yes,
G.
a G. And there's sort of acronym for memorizing the classification. Usually it's something like "Oh, be a fine gal or girl, kiss am I."
Oh
And the
yeah.
next one is lips. Blah blah, and it goes on. It gets a little bit silly for the things, but
Oh, why do cooler stars have more absorption lines? Do they contain more of the heavier elements because
I
of that, or
I don't think so. So I'm going to speculate here, Landon, and I
Mhm.
want to see if this sounds crazy. I think it's not about metallicity, basically, would be another way of saying what you just said, Ness. I think it's about the stability of molecules themselves
Mhm.
in the photosphere of the star. For
ah?
very, very, very hot stars like Sirius, the light that you're seeing is coming from a surface that is just so hot that molecules just aren't going to exist, and a lot of these absorption lines, probably most, are molecular absorption lines. Is
Yeah.
that correct?
Yeah, and in fact, so when you talk about mini molecules, they're referring to the existence of molecules and other, higher order compounds um, surrounding the star, that are able to, or why? Because either it's low enough temperature that those molecules can form and be stable, or there's additional material around that is being excited, so we see the existence of those molecules as well. But you go from very high temperature, very energetic things where the ultraviolet light, it's been blue shifted to purple, way up into the violet and ultraviolet. So any kind of molecules nearby would be effectively destroyed, broken apart by the radiation from the star, down to stars that are very weak and are just smoldering, for which complex molecules and dust can settle in close. Next, moving on to the next one.
Oh, there was a question in the chat that I wanted to. So Katina asks, is it consensus that all stars start out with the same elemental composition?
No.
No.
All
And
stars start off with their clouds, and their clouds can have various composition. And in fact, over time, those clouds that they're formed from have had material. They've been sort of, the snow has been dirty, dusted.
yeah, the time when that would have been the most true would have been for the very first population of stars, called the population 3 stars, because before that there wasn't any of the mechanisms that we're going to be talking about for creating the heavier elements. So basically they all started with the same cards. They started out with 75% hydrogen, 25% helium, and then very trace amounts of other light
Lithium
elements.
and so yeah.
But as those stars died and sort of seeded and provided some heavier elements for some of the other stars, then the second generation of stars, called the population 2 stars, excellent naming convention, 10 out of 10, those would start and have more heavier elements. It might have some calcium or something in it potentially, but it doesn't really, it's not really a big driver, as I understand it at least, of how the star itself evolves.
This is actually a question I have also with regarding the CNO cycle. You need to have carbon to start the cycle. But when you have the first, like the population 3 stars without any heavier elements to start with, were they unable to start the CNO cycle at the beginning, basically, because they didn't have the carbon to start the CNO cycle at the time. I don't know if it affects the way they behaved, because they lacked any carbon to catalyze this CNO cycle.
That seems plausible. I imagine that is an area of active research.
Like I would imagine that the population, like when the population 3 stars start to fuse helium into carbon, then the CNO cycle would start immediately, basically, or almost immediately. I would imagine that. Yeah.
Real fast. I know we're gonna get to it later on. What is the difference between a population 3, 2, and 1 star?
Yeah.
It started off by saying the population of stars we see, like our sun, was seen as the first population, or population 1. It's unfortunate numbering, and so the stars that were part of the process that was the generation before were population 2, and in population 3 are the generation before that. Now, that generation is not like you have in biology of parents, grandparents, and so forth. It's more about the era of star formation. So
Yeah,
the stars that form this time are population 1.
Yeah, wouldn't that makes more sense the other way around? Is my brain?
I know, but it's the numbering that I talk about, and even the population, because it's not true to say generations of stars. They're not biological.
I think the metallicity was first described, and then it was later found to be they are like the population 1 stars are a bit older compared to the population 2 stars, perhaps. Maybe the naming convention was realized before, or was established before it was realized that population 1 stars are younger than population 2 stars, perhaps.
Yeah, it's called that because you had a population that was understood, and then they noticed these lower metallicity stars, and they were like, this doesn't fall into the first category. I guess we need a second category.
Yeah.
And
so
it's
another population, right?
Yeah.
But they didn't really realize at the time about the metallicity of stuff that it was a function of the evolution of the cosmos. It was just seen as the other population, and then the speculation of even another population, and then it became a timeline, and people said, well, by that time the numbers stuck. So. And it is a case that astronomy sometimes has nomenclature that we later on regret, but that's the way it goes. I mean,
also, about this, I think we need to move on this diagram, the Hertzsprung-Russell diagram.
Yeah, so good starts. Okay. So who wants to talk about this?
Well, I made this slide, so I think I can. Like, it's okay, you can see the main sequence star. The main sequence on the diagram is called if I pronounce it correctly, the Hertzsprung-Russell diagram. It basically shows all the stars on a plot compared to the color on the x-axis. I think on the left it's hotter, and on the right it's colder. And if you go from top to bottom, it gets brighter. The bottom stars are very dim, and the top stars are very bright. It's a very, very convenient way of plotting different stars based on their luminosity and temperature. And you can see the main sequence stars are basically the stage of when the stars are the youngest, when they are fusing hydrogen and helium at their juvenile or adolescent stage almost.
And our star is still on that stage right now?
Yes. Our star is still mainly fusing helium. Mainly fusing hydrogen into helium today, yes. And you can see at the bottom right, there are red dwarfs.
Yeah.
And they will fuse hydrogen into helium over trillions of years until they become white dwarfs. And then as you move up a bit on the main sequence, between solar masses of 0.6 to 10 solar masses, those stars will eventually enter the red giant phase. And you can see the red giants a bit above the main sequence on the diagram. Those are red giants.
Yeah. The main sequence is the main sort of diagonal wiggly line. there are other things on here, other clusters that are not the main sequence. The main sequence is where a star lives its most of its
First stage.
life. Yeah.
First, also the first stage. I think.
Yeah.
You're also at most of its life. Yes, exactly. Unless you are talking about very massive stars, then it's a very short life.
Yeah.
Yeah.
So just as you're describing what's showing on this diagram, so from left to right we have the spectral class, and that means that the things on the left are the higher surface temperature stars that also tend to be bluer in their spectrum, versus the other side that tend to be redder, right? And you see on the bottom there's this thing called color, B minus V, right? You take the brightness of the star in, let's say, a blue spectral line, compare it to let's say the visual spectral line, and the difference is if it's negative, towards negative, it tends to be bluer. If it's more positive, it tends to be more red. So first is the spectral class, going from one side to the other. The other thing is luminosity, and this we're talking about the absolute how much light is a star putting out.
Yeah, how many photons? Photons? Yeah.
Yes. To do this, you need to know how bright the star appears and how far away the star is. So when it began to plot the color of the star, with the x-axis, to the estimated luminosity, the y-axis, it began to show things that are happening. And I want to say that historically, this came, it's called the Russell diagram. They start off with the Henry Draper catalog, whose data came from the work of an amazing astronomer, Antonio Murray, who was a very well-deserved Cannon Award recipient for her work. She did a lot of fundamental cataloging and measuring of many stars back before the eras of computers, and did some amazing work whose data was cataloged by Draper, who then was converted into this HR diagram. And so I do want to recognize Antonio's work for giving us a really fundamental. A lot of what we're talking about, the foundations came from her hard work up in observatories, doing very, very detailed work to give us lots of data about stars.
I think one last thing to mention is the white dwarfs at the bottom. Those are the remnants of low to mid-sized stars. Like after they have become red giants, the remnants will become white dwarfs.
And so you probably want to go to the next slide. I'll help on that.
All right. Yes.
Talking about.
So, in terms of where they start off in the main sequence, and they tend to turn off that spot, it happens to depend upon mass of the star as well as their age. And so you'll see in the diagram where the life of the star tends to veer off to the edge, right? And why is that? Well, we'll see when stars go through phases. I mean, particularly massive stars go through phases where they balloon up. While there's a lot of energetic stuff going on in the core, the star expands quite a bit, so its surface area is much larger, and so it tends to cool. It appears to be cooler because you have the same amount of energy in a larger surface area.
Yeah, so they become brighter, but also cooler. So they move to the top right, basically. They move upward and to the left on the diagram, right?
Yes.
And it's also shown in the diagrams here. Yeah.
Yeah, because remember, what's with the x-axis is color or temperature, and the y-axis is luminosity. So when you see, for example, the one star, what our sun will do, it will, as it goes into its giant phase, the surface area will cool down, but it'll become brighter because it's more energetic. Remember, again, the star, what's in a star is a balance between gravity crushing it and the action in the core pushing out.
Yes, and you can also see like in the on the left you see like a star clusters, and I believe that every star in the same cluster is roughly the same age, and you can actually see that as the cluster of stars become older, the more massive stars exit the main sequence stage earlier than the lower
Yes.
mass stars.
Correct.
And that's why you see the curve in the diagram. All the younger clusters are all on the main sequence, and then as the cluster of stars become older, then the more massive stars become the giants.
Yes.
And
yes. Another way of saying it is that where a star sits in this diagram is also a function of how they're formed and then how they go through how they evolve. Now, certain things like the Pleiades, open clusters, those stars are formed roughly at the same time, so they'll have similar, usually similar things. Clusters like Omega Centauri globular clusters are a bit more complex. In fact, some of them we believe may actually have been cores of dwarf galaxies, and so they're going to have a much richer set of things. So I would hesitate to talk about globular clusters. We thought for a while that globular clusters must be around the same age, but we started seeing in there things where they had lots of red dwarfs and brown dwarfs, but it also had we were surprised that they had black holes and neutron stars in there as well. Globular clusters are fun objects that are much more complex than just piles of stars. Next one.
Yes.
Okay, so we do have the notion of when the stars get more massive in their core, you can start converting helium into carbon. This is one of the processes. Now, our sun doesn't do this particularly well. In fact, it probably doesn't. If it happens very seldom. But
what
when
happens very seldom?
What
happens very seldom?
That you'll have helium fusing, right? Stars that are in the phase that our sun is currently in aren't really fusing much helium. But as the core gets more energetic, why? Because when the star starts running out of most of the hydrogen to fuse, gravity begins to win, crushes the star down, increases the temperature and pressure in the core, such that helium can start fusing into beryllium and carbon.
And that will happen in the sun when the sun is already a red giant. I believe we will cover that in the next slides.
Yeah.
Yes.
Yeah, but this is another process that goes on there. So next one.
All right.
So this is a good diagram talking about what happens as stars go through their cycles.
And this is the fate of medium stars, as our sun is also a medium mass star. This will happen to our star eventually.
Yeah. And so this is sort of showing that they start off somewhere in the main sequence. And stars like our sun tend to be kind of in the middle with average luminosity, average temperature. But at some point when they run out of most of the hydrogen in the core to fuse, gravity takes over. The star, gravity crushes the star. The pressure and temperature in the core increases. Helium begins to fuse, much more energetic. The resulting is that the pressure pushes the envelope of the star out. So the star actually swells up. because and this will make the star appear to be cooler, because you have much more surface area around, even though there's also going to be brighter as well. And so this goes into the red giant branch. But eventually, that star like our sun will do their helium fusion, and then, but if they have enough mass, such as this goes up to about 10 times the mass of the star, they'll actually begin to fuse helium and going into these other processes. So kind of go back and forth depending on how much mass the star has. So let's go to the next one. Probably is.
All right.
So here shows you the evolution of stars. Again, medium mass. So they're not brown dwarf smoldering things. They're not red dwarf kind of smoldering things. They're normal stars that go through to massive stars. So this larger diagram is probably more on the closer to the 10 solar mass stars than the 1 solar mass stars, where it goes through a red giant phase. Helium begins to fuse. It goes into another phase where you get even more carbon in the core, but then it essentially it runs out of ability to crush the carbon. The carbon not really engaging much in the fusion process other than CNO cycle. And so, but when stars go through phases where they start from hydrogen to stuff where you helium fusing to other stuff, every time they go through a phase transition, there's a much more energetic reaction that sends out a shock wave, and it tends to blow material off the edge. And so the term planetary nebula came from back when we didn't really know what stars were, and people with poor telescopes looked at these nebulae and said they kind of look like planets. So they're sort of planetary-like nebula. They're not planets, but the name stuck. What you see on the left, the star in the center, the very faint star in the center of that blue disk, is the star that caused the shell of material to be ejected, right? It went through a phase and it created this nebula, this sort of, they tend to be rings of stuff, so-called ring nebulas, I think is a better term. But they'll eventually run out of things to do in their core. They will cool down to white dwarfs, and you see the dashed line where they basically tend to, they get very hot from the fact that they've blown off all the material. You just have sort of a smoldering core, quite hot, and the core radiates out into space and cools down.
And I think the reason why stars like our sun becomes a red giant is because of when the helium is produced, it becomes an inert core that is unable to fuse at first. So in order for fusion to continue, the core of the sun has to, or first, I think the inert helium core is unable to withstand the pressure, so the star pushes downwards by gravity, and that increases the temperature of the outside of the core, and that allows hydrogen to continue fusing as a shell surrounding the inert helium core. But eventually the helium core itself becomes fusible into carbon.
I think just to emphasize the sort of core thing that's happening here is when the fusion dips below a certain amount, you no longer have enough energy being produced to push the outer layers of the star out, and they will contract, and that increases the pressure and increases the heat until a new type of fusion can start again. So it's always this balance, and when the star changes between fusing one type of material to another, at first it can't fuse that new type of material, but that means that the star starts to contract. and that's why it becomes capable of fusing the inert helium, which it previously was unable to. And that happens throughout, like that process is kind of the process that determines how a star lives and dies.
Yeah. So let's go on to the next one, the next slide. And here with this next thing, the next page, I want to basically talk about the difference between nova. This is and a certain type of supernovae. So here we're talking about the end cycle of medium mass stars. They're the so-called white dwarf. This is after they have gone through their how many stages of fusion, and the result is you get a smoldering ember, which is dense. It's a collection of atoms that are really packed together, not neutrons, but atoms, and under very degenerate conditions. When a white dwarf is in a binary pair relationship, and a lot of stars are not single stars like our sun, but have pairs of stars or clusters of stars. It's often the case that the two stars don't necessarily go through their phases at the same time. They might have slightly different times. So you might have a pair of stars where the one star has gone through its phase, it's ejected its shells, it's gone through its flashes, it turns into this dense white dwarf. Now the other companion, a little bit later on, goes through its giant phase, but now it's got this white dwarf next to it, and material that's been pushed out by the star falls into and on the surface of the white dwarf. Now, that what is that material from the primary star? That is the star that went through its giant phase later. It's hydrogen. So hydrogen tends to build up on the surface of the white dwarf, and it gets thicker and thicker and thicker. The pressure gets bigger, 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 and at some point it begins to fuse, and you get a rapid burning, this fusing of hydrogen at the piled up on the surface of the star. Remember, and to a thickness where you'll get an explosive ejection, right? And it'll cause nova to occur. And there are stars that have sort of somewhat periodic ejections where they've got their companion feeding them material at a certain rate. It piles up to a certain depth, begins to fuse at the bottom, goes bang, and pushes out. There's a different thing that happens, however, because when it dumps the material and goes bang, some of the material stays behind. And so when it fills up again, it has a little bit less, takes a little bit less time. Eventually, there's enough mass that sticks on the white dwarf that it becomes goes beyond what's called the Chandrasekhar limit, where the mass of the white dwarf exceeds about 1.44 times the mass of our sun, at which point there is an enormous thing goes on. You get a runaway thermonuclear event, and it gets called a type 1a supernovae.
I was just going to say that the phenomenon where as a white dwarf approaches the Chandrasekhar limit, it's really fascinating, because when you work out the math, where the 1.44 solar mass comes from is when you do the math, you have a relationship between the mass of the white dwarf and the size of the white dwarf.
Yes.
And as you increase the mass, the size gets smaller.
Yes.
And
because there's more stuff to crush the atoms even closer.
Exactly. and the 1.44 thing is basically when, in a simplified version of the math, because obviously you're transitioning to the thing that kills it, is the size of the star, like it keeps on getting heavier and heavier, and it gets smaller and smaller and smaller, and then it hits zero. It hits zero size, and that happens at around 1.44, and because it just can't hold it anymore, and then it goes and it has what's called a type 1a supernova. And because type 1a supernova, by definition, occur in this way, they always occur at the exact same sort of point physically. They occur when a white dwarf becomes this heavy, which means that all type 1a supernova are very, very similar to each other.
Yes. And now there are actually slight differences. Yeah. And one of the things that my good astronomer friend Alex Filippico did was to help determine when they spot these type 1a supernovae, the speed at which it goes up in brightness and drops back down is a function of conditions in the star. The reason why. So while you might say if we call these type 1 supernovae the cosmic 100-watt light bulbs, some light bulbs might go some light bulbs might be in the 90 watts, some might be about 110 watts. There's a slight variation. And the speed at which which the supernova rises and falls is a function of whether it's closer to the 90 watts or the 110 watts. I'm speaking metaphorically. So what Filippico and his team did was to measure, look at supernovae that were close enough they can get good distances, watch their brightness curve, and basically calibrate. The calibration of stuff. So while the type 1 supernovae are the proverbial 100-watt light bulb, there's slight variations. And the variations can come from how fast the star was really spinning and other material that's in it that can vary the wattage slightly, as well as dimming and stuff. And so they were able to rule out the dimming by looking at spectral lines in order to look at the light curve to basically give it a much more precise thing. That was the key puzzle piece that allowed people like Adam Rees to discover that supernovae weren't as bright as they expected to be because the universe is accelerating. I want to mention as well the person Chandrasekhar.
I drew a thing to describe what you just said, Landon.
Okay. Sorry?
Oh
yes, please.
Yeah. So
Tapio Weasel is bringing out the whiteboard.
Yes. So in a type 1a supernova, you've got the supernova starts at some time, and as time progresses, it gets brighter and then it gets dimmer. And what Landon was just describing, I had sort of previously said that all type 1a supernova are very, very, very similar. And Landon was just describing the way in which they can be different. So this one, for instance, that grows faster and then decays, I'm assuming, yes. I don't actually know if it's the same.
That's right. That's right.
This would be a 110 watt supernova, whereas this one would be a 90 watt. But the relationship between these is a very sort of precise. You can correct for that basically, and you can sort of then replot all of these things with a normalized sort of unit of time. Maybe you choose a time unit that is related to something, and then all of those curves will, when plotted, you can basically figure out, even despite this difference, exactly how high the peak is, because if it goes up like this, even if it's very dim, because they measured it, Filippico measured it, that they all do the same thing.
Yes.
Or that they all follow a certain functional form, but the precise coefficients can be slightly different. And so this right here, and the ability to make all of those sort of line up on the same curve, is why they are so phenomenal as standard candles.
Yeah, and that additional precision allowed them to essentially determine the universe is accelerating, which is an awesome thing. I want to mention also, it is important to also mention Chandrasekhar, an extraordinary physicist. who had his mathematical treatment of stellar evolution was really quite fundamental. So the Chandrasekhar limit and formation of black holes and supernovae and so forth are all named for the mathematics that he put in place. I had a chance to talk to somebody who was Chandrasekhar actually lived between 1910 and 1955. I actually spoke with my colleagues who was with Chandrasekhar when he was doing the math to try to figure out what happens to the star, just as he was saying about the more massive the white dwarf, the smaller it was, and realizing if it keeps getting smaller and smaller, something's going to happen. And so he got somebody to go to the university library when it was closed to get various books, to get the tables about physics of degenerate matter, and realized that the star white dwarf falls off a cliff at a mass that he calculated 1.44 times the mass of our sun. Again, Cambridge mathematician, physicist, who has extraordinary contributions to astronomy. So thank you, Chandrasekhar. There is a X-ray telescope called the Chandrasekhar telescope, aptly named because the telescope tends to observe things that Chandrasekhar helped gave us some solid mathematical data. So I mentioned the next thing here is a fun thing happening about this nova that's going to come. We expect it to come.
Next slide. Yeah. Next slide is I think
Okay.
is that.
All right.
Yes. This is in the recent news. I noticed a few days ago that one star is bound to become a nova. One previous slide.
No. Go back. No. There you go.
That.
Oh, must have hit accidentally.
It's a T Corona Borealis. I think it's pronounced.
Yes.
Is the star.
Yes. It is in the constellation Corona Borealis, and it's sort of like it's visible in the primary from the northern hemisphere. So it's a nice sort of sea ring of stars. That looks kind of nice. But there is an object in that region, not on the ring, but off the ring, which has undergone nova in the past. It's again one of those things where this is an artist's conception, where the companion star is feeding material on top of it, and it feeds at about the same rate. So at some point, it will undergo this nova flash, and we're actually waiting to watch it happen. Because we can gather some really useful data of what happens with novae, knowing. So we're anticipating this happening. Given the history of stuff, it should happen sometime this year. It has gone. It happens before it goes. We see that it kind of has a dip in brightness and it'll go up bright enough. It actually might be bright enough that you could see it, certainly in binoculars. And likely if you're in a dark sky, even visibly.
It will appear as a new star, basically, just like maybe not something out of the ordinary, but it's just like, hey, I did not notice that star before.
And so it won't be you to see it. You probably, although this is probably, you probably need to go into a dark sky without the moon showering. To see it. But if you do, it'll probably be one of the most distant stars that you've ever seen, unless you are fortunate enough to see 1987A, which is a supernovae. So it's worth looking at if you happen to watch it. And again, we will be looking at it from a number of instruments, actually waiting for the announcement that, hey, it's taking off in brightness, and telescopes will sit there and watch the whole curve in great detail.
Is 1987A the furthest star you've ever seen?
Yes, it was 187,000 light years away, approximately. And the nice thing about that, I was on the ground in Mount Stromlo Observatory in the Australian Capital Territory about 19 hours after it was discovered. I had always had a clause with my employers that says that I get to go anywhere in the world whenever there's a supernova that reaches naked eye brilliance, right? And I would tell people, like if I were best man at a person's wedding, I said, I got this pocket detector. If it goes off, I'm leaving you and heading off, because these are extraordinary events. And I was fortunate enough to watch that supernova actually change in brightness. So that brightness curve that you drew, I actually watched a star do that. I watched it change in color and change in brightness before my eyes, hit the peak and go down. It was.
How long does it do that to reach the peak and become dip down again? How long does the curve last?
Yeah, well, I guess the peak was about 2.5 days, 2 days or so for that thing. And of course, the tail is very long, right? I was able to see in a modest-sized telescope the supernovae about 2 years after the event. But the rise is actually in a matter of hours, days to hours, depending upon circumstances. So next.
Yes,
Right.
next slide.
Next slide.
So, really massive stars, well beyond 10 solar masses, go through a number of cycles. We mentioned the helium to hydrogen to helium to carbon, but if there's enough mass, the carbon will begin to undergo a chain, and here we see the carbon going up to going through the process, and usually what's happening is essentially you're having helium nuclei become the dominant thing that fuses. So rather than, let's say, carbon fusing with itself, you have helium nuclei slamming into carbon atoms that build up to form neon, and then eventually it gets to oxygen, to silicon, and then to iron. And so this process of what's happening in these stars is as it goes through their phase transition. So whatever's happening, let's say, for example, the carbon in the core gets to be exhausted, mostly exhausted. The gravity begins to win the tug of war and starts to crush the star. The pressure and temperature in the core increases, and now you get neon in action. And then you can get silicon, and then you can get into iron and on down the line.
But it doesn't continue forever.
No.
And that's what the middle figure is for. You can see that, on the left, you see lighter elements being fused, releases energy. But up to a certain point, the opposite happens. When you start to try to fuse iron, for example, or nickel, when you attempt to fuse that, it doesn't release energy anymore.
Yeah. And I'd say, well, why is that? Well, atoms like oxygen have, nuclei of oxygen have 8 protons. If I remember is that right? Oxygen is...
Yes.
Is 8, and it will so when it has many more positive charges, it's much more repulsive, and it takes more energy to get something close enough to the atom where they fuse. So the time you get to iron, which is around 26 protons, if I recall correctly.
Yes.
You have to do a lot of work to get anything that's other than a neutral particle close enough to the nuclei for it to fuse. Now, I should point out, we're not talking about fusion like a bunch of billiard balls that are sticky. What you really have to do is to get the nuclei close enough together that quantum mechanics takes over and they fuse and
yeah.
What's ultimately
Right.
happening, not to belabor the point too much, but what's ultimately happening is that according to quantum mechanics, you have a bunch of particles and they're all interacting with different energies, and there are different states that will be stable. And if you get it close enough, then suddenly it's more stable if it just goes together. But that's quantum
It's
tunneling and all of that stuff.
Yeah.
it's also like a fight between the electromagnetic force and the strong nuclear force. Like if two
Yes.
nuclei are far
Exactly.
apart from each other, the electromagnetic force forces them apart from each other. But
Yeah.
if you manage to get them close enough, the strong
Yes.
nuclear force might be able to bind them
Yeah.
permanently.
Yeah. Yeah. That's pretty good. I like to refer to them as interactions, where
Sorry about that. Yeah.
no, that's fine. That's fine. Nuclei that has positive charges that are far apart, the electromagnetic interaction want to push them away. If they get close enough, they can actually quantum tunnel, and the strong nuclear force says, let's merge. And so
Also,
on the graph here, the blue section where energy released is where fusion of nuclei is exothermic, right? Remember from chemistry, exothermic gives off stuff, right? Gives off heat, gives off energy, right? The left side energy, the other side is a case where if you force fusion, it is endothermic. It'll absorb.
Mm-hmm.
Um,
Yeah, so you'll
I
end up
have
if you fuse two bits of iron, you end up you have to add heat to it. You don't get heat out. So that
I've
has
heard that iron and nickel are like the most stable elements.
yes.
Like they have the how do you call it? They have the most the highest binding energy per nucleon, basically, right?
yeah, to some
Yeah.
extent. And so if fusing hydrogen is the dynamite, the nitroglycerin chemical reaction, when you get beyond iron, you get things like reactions like ice and salt, where it absorbs, it takes energy, it's into it, and so remember, stars are the balance between the action going in the core pushing out and gravity coming in. When you get to the point of iron and nickel, the fusion reactions are now no longer giving off energy, they're absorbing energy. And the result is that as the star begins to fuse those heavier elements, it no longer has outward pressure and the star collapses. And in fact, it collapses rapidly. These stars that begin to fuse iron and heavy elements, they're some of the largest stars you probably can see. They're very, very large stars in terms of radius. But when they collapse rapidly. They end up collapsing on a matter of seconds, right? The set there. But you're going to say something?
Is that why those elements can only form in explosions or novas?
It's why they're only formed efficiently then. You could still form them,
Yeah.
but
We'll get to that a
other
little bit
things are
later.
happening.
A little bit later on those other cycles. So let's go to the next page. We'll get to that spot. I just want to point out the phase of these massive stars. The more massive the star, the shorter its life. So a star like our sun,
the top right table. Yeah.
a star like our sun will last on order of 10 billion years. If you talk about a red dwarf to brown dwarf that's be a tenth of the mass, it'll last, instead of 10 billion years, it'll last trillions of years. Whereas, for example, a star that's about 3 times the mass of our sun, instead of lasting 10 billion years, will only last maybe a third of a billion years. By the time you get to something like 60 times the mass of the star, you're around to 3 million years. So you've cut the life of the star dramatically.
It's like even though they are like 10 times more massive, they fuse up stuff 1,000 or maybe even more times
Yes.
as fast.
Yes.
Yeah.
Another thing to say is that the rate at which it goes through those stages is an exponential rate. So here we have a fate of a, let's say, 25 solar mass star. So it has enough mass to go through all of its stuff into getting iron in its core. And you see that maybe the hydrogen phase might last. Remember, these stars are a 25 mass has a lifetime of only maybe, let's say, 7 million years. Right? The hydrogen phase lasts for 7 million years. The helium phase lasts for 700,000 years. The carbon oxygen lasts for about 600 years. The oxygen to silicon, 6 months, half a year. Silicon to iron, 1 day, and the collapse of the star happens in a fraction of a second.
I've also seen that when a very massive star exhausts one previous element, it becomes a giant. It becomes bigger, and then when it starts to fuse a new element, then it contracts again, and then each time it transitions to a new element, it oscillates basically from a supergiant to or a smaller. Do we have any known star that is known to oscillate like that, to become supergiant and then back again, and then or maybe
we certainly watched stars go through these phases, and of course the supernova is probably the massive stars is probably the last most dramatic of those phases. So we've seen stars undergo phase transitions, and again, it's believed that things like the star Betelgeuse, or Betelgeuse, depending on your pronunciation, is a star that's going through unstable period where it is potentially transitioning to the next phase. And so we see stars go through when they go through that transition, like let's say they go from carbon to oxygen to the oxygen to silicon phase. It's not it goes as it approaches it gets to be unstable, right? That the star begins to collapse because there's not enough action in the core, heats up, it pushes back a bit, goes back and forth, but eventually it goes ka-chunk. And the core goes down, but the energy of coming from the core goes way up. So the star brightens and pushes its outer envelopes out much further. Go ahead.
So we still have plenty of time before our star transfers into a helium carbon fusion star.
Yeah, given where we think it is, it has about 6 billion years, 5.5 billion years, 5.5 to 6 billion years. So it's got a while before, and it's going to go to the helium fusing shell. It doesn't have enough mass to get into the carbon fusing shell.
Also, we actually will run into problems sooner. Like in 500 million years, the sun will become it won't become a red giant proper, but it will still be a lot warmer or hotter than it is right now in 500 million years.
Yeah.
And it might become too hot to sustain complex life, at least in 500 million years. Yeah.
Now these massive stars, the core actually becomes rather small compared to the size of the star. So in this particular case, we have a star whose core that's in the central spot is just starting to get to iron. That core region might have around a 10,000 kilometer diameter, where the outer region of that core is still hydrogen fusing, then helium, then carbon, then neon, then oxygen, silicon, finally iron. But that 10,000 kilometer core is inside a star that's 1.6 billion kilometers in size. All the rest of that stuff you see, the supergiant, is the outer envelopes of the star that is probably mostly hydrogen with helium and carbon oxygen fusing it, but mostly hydrogen. But the action is a tiny part in the center of the star.
How much of the mass is in that core? Is it also a very small amount of the mass? Is most of the mass in the envelope?
There's a fair amount of mass in the core, but not all the mass is there. And I'm trying to remember the ratio. Is that coming to mind? Sorry,
Yeah,
someone
'cause
wrote.
But it's probably a lot more than the ratio between the volume, right? Compared
Correct.
to the volume.
yes, yes,
Yes.
necessarily.
The,
But
the core is much denser than the outer non-fusing shell. Yeah.
my intuition would be that the vast majority of the mass would be in the envelope. But if I could believe that I am wrong about that.
Yeah, I won't speculate. Someone else who watching this thing can leave a note saying you forgot da 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 da. Right? I'm sorry. There's lots of stuff to remember. This sort of thing. Let's go to the next one.
Okay.
So massive stars that start off in a nebula, collapses. You get a star on the main sequence, but this is a big tubby star that goes through supergiant phase. It finally ends in what we call a type 2 supernovae. And depending on how big it is, you could form a weird thing called a neutron star, or even weirder thing called a black hole, with a lot of stuff being pushed out. And again, these supernovae are quite spectacular events. What we see on the right hand edge is a picture of the Crab Nebula. This was a star that went type 2 supernovae in 1054. It was a star that was seen basically this guest star that showed up, and number of civilizations around the world watched this star. This star actually was bright enough that people could see the star in the daytime, and it was visible for I think almost a year or two. Is that if I recall correctly?
I've seen it too. That it was visible, maybe not visible during the daytime for a full 2 years, but it was the supernova was observed for 2 years, I believe. Yeah.
So how close to us was it?
What's the difference? Isn't the Crab Nebula only like 1,000 light years? I
have no idea.
It's in our galaxy at least. Otherwise, we wouldn't be able to observe.
Yeah, it was in our galaxy, and it's the distance estimates around 6,500 light years. 6,500 light years. 6,500 times 10 trillion kilometers.
How frequent are this type of supernova in our galaxy? Like once every 1,000 years or once every 10,000 years?
We believe the rate on the Milky Way is about once per century, but maybe a little bit more frequent. Do you remember?
Oh, that's actually a lot more frequent than I first
that
thought.
Sounds pretty frequent.
Because supernova outshine their own galaxy, right?
And now the thing is that in our galaxy we can have supernovae going off on the other side.
Yeah,
we have supernovae going off behind dust clouds that we don't see, right?
Right.
Typical visible supernovae to the Earth happens at an average rate about once every 4 centuries. But we only see a little bit of stuff. There's a lot of the central part of our Milky Way, or most of the stuff that's hidden by molecular clouds that absorb light. So you talk about seeing something. In a typical, when we look at galaxies out there, on average, I think it's around once per century. But there are galaxies that are much more active than other galaxies. So don't take that as that hard and fast rule. What it does say is if you want to catch a supernova and stare at a galaxy, you might not want to do that. You might want to actually stare at lots of galaxies. In fact, what Alex Filipinko and his student team did with the Cassini telescope was to build a robotic telescope that would go and take pictures of galaxies, and the software began to look for dots that then the undergraduate students would look at, and if the dot looked supernovae-like, they'd go back and look at it again, and look at it again and again, and build the brightness curve and say, supernovae, right? So they were the first sort of supernovae detection factory that for a number of years were the record for seeing. And so they had rates of like 100 per year, what they thought was doing pretty good. Now there's much more efficient telescopes that can find supernovae at quite a good rate.
Okay, so
Is-
on the left side, the universe recycles itself.
Well, we'll talk about this in BE4.
Okay.
What's happening to the ejection stuff.
Also, like one last question before we move on to the next slide. Is the Crab Nebula a neutron star or a black hole? Do we know that?
It's a neutron star.
All right.
And how do we know that? Well, I've actually seen the neutron star. One of my very first observations was to take the Fremont Peak 0.8 meter telescope, and I put basically a fan blade that was oscillating around 30 times a second, a shutter, right? It's a rotating shutter, and I put it in front of the beam where that central spot is. I could sort of point at the spot. I can tell you where the spot is, but it's hard to see in that mesh. There's a dot that's actually the neutron star, and when you scan at a rate of 30 times a second, the star's blink rate about 31 times a second begins to strobe like the wagon wheel effect. And
that's
so
amazing.
You drift across, you have this rotating shutter, and all of a sudden you see the star going in and out, in phase, out of phase. So you can find the neutron star that way. It was the first visible sighting of a neutron star done that way.
Is it possible to view the reflection off of the nearby clouds in the nebula strobing like that as well at all?
Well, most of the glow of the nebula is not due to light coming off the neutron star. There's very little. It is electrons being accelerated.
Yeah.
If you think about the neutron star has this massive magnetic field that's spinning at around 31 rads a second. That magnetic field acts like waves, and those waves catch free electrons, and they surf the wave just like surfers on a wave coming to shore, and accelerate. And accelerate to the point where they go faster than light travels in the medium, and you get signal radiation, as well as near the edge, right? And the other things where they're slamming into nuclei and causing them to transition. And so,
also, accelerating charges emit light.
Yes.
Like just on their own. Bremsstrahlung, I believe it's called.
So that blue glow you see right there in the image on the right, that's Cherenkov radiation, basically.
No, only in the center. You have to
only in the center.
You have to see things like, if you look at things like the region is, because it's dominated by other stuff. The blue glow there is mostly that is the Bremsstrahlung radiation, other things, other effects. But Chandra-Shekhar telescope looking down towards the center will find the region in which things are being accelerated quite nicely. But anyway, it's a nice spot, and that was the first time that we visibly detected a neutron star spinning at a nice rate. So let's go on to the next. So type A supernovae. So the question, and if you know the answer, don't give it out. To the chat is which of the following would be brighter? Okay, we have two things. One, we have a type 2 supernovae that's occurring at the distance of the Earth's sun, about 150 million kilometers. Okay. The other is a detonation of a 1 megaton nuclear bomb pressed to your eyeball. Which is going to deliver more energy to retina? The type 1A supernova at a distance of Earth's sun, or the 1 megaton bomb right next to your eyeball?
Well, I think both of them would fry it, would melt it.
So I guess for the chat, if you're listening, type 1 if you think the supernova is brighter. Type 2 if you think the 1 megaton nuclear bomb will be brighter. Type 3 if you think they're about equal. So 1, type A supernovae, type 2 supernovae at 1 sun distance. 2 is megaton bomb next to your eyeball. 3 would be about the same. We got 1s, some 3s. Survive. Well, I mean, let's talk about the fact that it's the energy delivered to your retina, not that you might be able to think much about it.
You won't survive.
Either way.
Don't do this at home, kids.
Yes. Don't do this in your backyard or even do this in your solar system. This is not a... So, okay, we got a couple things. Let's go to the next slide. I'll give you the answer. So the answer is that the Type A supernova is over 1 billion times more energetic.
Even at that distance, even
at a distance of 150 million kilometers, your retina would receive over 1 billion times more energy than a 1 megaton thermonuclear device pressed against your eyeball. It is just insane the amount of energy these supernovae put out.
Is that's total energy? So that's integrated over the duration of the supernova?
This is peak energy.
Oh, okay. So it's power is.
Yeah.
Because I was thinking, if it's 1 billion times, but it's spread over a week, then the bomb would win in the split second.
And we're talking about the flash, right?
Yeah,
the flash is going to occur, and you'll see a blinding flash of light, mostly gamma. You'll also get a non-trivial radiation dose of neutrinos.
Yeah, I was going to ask, like, would you be able to feel them?
Yes, you get a lethal dose of neutrino radiation.
Well,
but you also, the problem is you get other things happening too.
That's scary. Like when you hear lethal dose of neutrino radiation, that's a scary.
You have other problems at that point. Yes.
Well, for the second one, wouldn't the bomb poke your eye out so you'd be blind anyways?
Yes, but you're dead both ways.
It's just that in both cases you're turning biology into physics. Yes. And in one case, you're turning it into exceptionally exotic physics, as opposed to just normal exotic physics.
Like, I have a question.
Sure.
Would the Earth remain a sphere, or would the Earth itself be blown to bits, basically?
Blown to bits.
Right.
Blown
to bits.
The supernova, sun won't go supernova. It doesn't have the mass to even, only gets to the helium phase. It doesn't have the mass to get all the way to the fusing.
I guess the only difference that I'm aware of is for the bomb one, it would happen to you right away, and the nova one would happen to you in 8 minutes, give or take.
Yeah.
Well, yeah, but once it started happening, it would still happen instantly.
Yeah. I like to say that both happen now.
Yeah.
I use it more of a general relativity thing. When you see the flash, it's happening to you now. Yeah. You're now, because remember, no one has an absolute clock. There's no absolute frame of reference. When you see a supernova goes off, it's happening now. You're now.
Okay.
Even though, for example, the Type 2 supernova that occurred in 1987A in the Large Dimensional Dwarf Galaxy Cloud, it took 187,000 years for the light signal to propagate. It happened when it happened was 1987. That's our now.
Okay.
To say, oh, it happened 187,000 years ago. No, if you were next to the star, yes. But for us, it happened in 1987. That's it. All right. Next.
Never mind. I had a question about the Earth being blown to bits, but this is just a minor question. I we can move on. Just to hopefully we won't be. Hopefully we won't go over time. Sorry.
Yeah. So the summary. You have these molecular clouds of gas, doing its normal stuff, hanging around. You typically have some kind of shock wave combination with a bit of more density that'll cause things to collapse to form a star that enters the main sequence. And depending on its mass, it'll be a brown dwarf that just smolders for trillions of years. A Loma star that can do like 10 billion years. That might go to a red giant phase to form a white dwarf that could, if it has a companion, do its nova thing until it gets to go supernovae, or just a normal white dwarf that blows off its rings, forms a white dwarf, and then eventually the remnant, which is a black dwarf, basically a white dwarf that we can't see.
And those don't exist yet.
Yeah. Any white dwarfs that are around are still hot and smoldering. They have not had a chance to cool. Massive stars.
Is it just the residual heat that keeps them warm? Like,
Yeah.
Only that. Only that.
Well, there's probably a little bit of things going on, but mostly it's heat loss. Glowing, right? Massive stars go through phases. They'll eventually do when you get to the point of iron in the core, it's game over. The thing collapses in a fraction of a second, and you get a supernovae. And depending on the type of supernovae and the mass, you either get a neutron star or a black hole.
I can see on
the.
the.
Also, this is not a complete diagram.
Yeah.
There are exceptions to the rules, which are very interesting. And if we put all the exceptions in, this diagram would get so busy that.
Yeah.
So there are other things that can happen.
There is my understanding is there is a type of supernova, a pair instability collapse,
Oh,
I
yes,
think
that's
one or
weird.
something, where it just annihilates itself. Like
Yes.
you don't even have a remnant at the end.
I actually included a slide on that. Yes, later.
Yeah.
I believe.
So-
I see. Okay. Yeah, we
But
can
this
move
is the
on.
main thing, right? At the birth of a star, depending on its mass, it has a fate of just a smoldering or normal star that goes through dwarf phases that may or may not go nova or supernova, depending on a companion, or massive stars that go bang, and depending on the bang, it usually forms a black hole or a neutron star, depending. That'll form a nice X-ray emission thing or a pulsar, right? Let's go to the next one here.
Yeah.
All right.
So again,
That's the same figure. Yeah.
some summary of the cycles of stars. And we'll talk about in BE4 the cycling process to where deaths of stars help form new stars.
The circle of life. No
we can also perhaps mention right now that as more cycles happen, the star-forming cloud, the nebula, become more enriched in the metals, and thus the stars born from those nebula are higher metallicity.
And they also get the nebula gets to be blown out the bubbles more, and so it's interesting. So let's go to the next one.
Okay.
So it is not correct to say that all the heavy elements are formed in the deaths of stars. I mean, Sagan's "we're all made of star stuff" is a nice poetic thing, prosaic expression, but there are things that happen that are not fully dependent upon supernovae. Certainly, you have processes in the supernovae that form the elements here, but perhaps do you want to go to the next one? Let's any comments on this.
This is a very detailed slide. So, if you want to skip this, then I'm fine with it.
Yeah, but there's a lot of interesting things for nuclear physics.
Yeah.
And I would look at this and suggest you look at this in more detail. What happens? But if you talk about the from the periodic table, remember that Big Bang fusion. We discussed that, I believe, in BE2, if I'm all correct, if I remember correctly, had hydrogen, helium with traces of lithium. That's the blue. We do have dying normal mass stars. That stars that don't go supernovae can give you some lithium, carbon, and nitrogen. Most of the beryllium actually comes from cosmic rays, but that's a different story for a different show. The green and the blue are the results of massive stars going supernovae or white dwarfs going bang. Right, and you could see that up to about krypton rubidium, it's coming from original primordial material, dying low mass stars, and supernovae. But once you get well up into starting like with element 44, bringing things like platinum, gold, some of those fun materials, they come from merging neutron stars. One of the things, and we'll talk a bit more about deaths of stars in BE4, but one of the things that can happen is when two neutron stars find each other, if you will, and collide, spiral down and collide, weird things happen. Really weird things happen. And in fact, let's go on to the next slide.
Real fast, isn't there more elements in 92?
Yes, but most of those elements beyond 92 have such short half-lives that you won't really detect them out in the universe.
They're not they're not naturally occurring, I think the
I have also a question about the yellow is dying low mass stars like our sun basically, and our sun is unable to fuse heavier elements or elements heavier than like oxygen and carbon.
Yeah.
But why does dying low mass stars produce like these heavier elements like mercury, for example? Like how does it happen?
Well, one of the things that can happen in those stars is there's some fusion going on, and the result of the process of helium and nuclei mergers can have some material being formed in lower mass stars. Now, low mass probably is a little bit of a misnomer here. What we're really talking about is lower mass stars than simply ones that explode. So you can get stars that say that maybe don't go supernovae. They're under the supernovae limit, let's say.
But they still
produce. But they will have fusion going on, particularly as they go through the end of life. There's some fusion that goes on that will form some material. It's possible.
Yeah. All right.
Anything? Any comments? I mentioned, by the way, on that thing that those gray elements were elements that are short half-lives that we don't detect them. This is really talking about stuff we can detect on the cosmos. So when neutron stars collide, they do really weird things. One of the things that we did with the Archetype cluster was we realized that the shape, that it's incorrect to say that neutron stars are these two billiard ball spheres that smash together. They end up deforming against each other and having tails. So if you look at this artist conception, which came from simulation data, you see that there are two blobs with these tails that look like sort of crook-neck squash tails, little edges on it. So you see that kind of like commas, but I think of them as more of a squash. The bulbous squash.
A tadpole almost. A tadpole maybe.
Yes. Yeah. And so the squash tails are a result of the fact that space-time is very twisted around these things. And the result is that when the actual neutron stars merge, excuse me, when the neutron stars merge, those tails, the tail of the squash, snap off and recoil and spray out. While maybe about 70% of the mass of the neutron stars merges, about 30% of the mass recoils and gets flung outward. Now, what does it mean by that? You have a tremendous amount of neutrons being flung out at relativistic velocities. Neutrons by themselves, without the benefit of weird dynamics, without the benefit of nuclear reactions, will decay. The other thing they'll do is they'll slam into nuclei because they're going at relativistic speeds, and will boost they'll hit nuclei and cause chain reactions to take them all the way up through uranium and beyond, right? So if you go, so when this stuff sprays out, stuff gets radiated by neutrons. Neutrons will decay. We'll see that as well in evidence of stuff and one of the things that gold standard we're looking for is a neutron star collision where we can visibly see the result of the decay of the neutrons. So I think isn't the half-life of a neutron around 600 seconds? Around 10 minutes? Is that?
It's it's like 10 minutes.
Yeah. But before the 10 minutes, it has plenty of time to slam into other material. What other material? Well, clouds around the event, right? And stuff gets radiated and it's boosted up. Now it will produce very heavy elements, but elements that are more massive than uranium, had more protons, decay very quickly. So yes, in this neutron star collision, you'll have everything up through 118 and beyond being created, but those things are so short that they decay almost instantaneously. We'll go to the next one.
All right.
So the simulations of merging neutron stars, a lot of weird things happen with the result of the magnetic fields and the mass, right? A lot of mass gets ejected, but most of it forms. In this particular case, we have a black hole forming, and black hole forming does weird stuff to the space-time, but the magnetic field does weird stuff as well. And the result is a very, very sort of twisted thing. And these mergers, right? You see two neutron stars, their diameters are in the order of maybe, this was showing a 18 kilometer diameter. No, the diameters are around 27 kilometers of the neutron stars, separated by 18 kilometers. So they're about ready to collide. Within a matter of milliseconds, they collide, this case forming a black hole and really twisted, weird thing. I'm going to show you, let's go to the next one here.
Okay.
In particular, this is showing the magnetic fields and the mass getting really twisted. The space-time gets really warped. And I want to show you a simulation that we have, if you don't mind.
Sure. Right.
I'm going to share the screen and grab this stuff. I'll show you.
1 second.
Okay. So what we're seeing is a simulation. There are two neutron stars that are about to merge. In this simulation, we are seeing two things. We're seeing the distribution of mass. This is going to be on the left-hand side, and on the right-hand side, we'll see magnetic fields. So we have this arbitrary unit scale of the mass on this side, and this side of the magnetic field. So when we start the rotation, we see that, for example, as they pass in, we're seeing the effect of the magnetic field being twisted as well as material. Right? The magnetic field's getting messed up. Because remember, these neutron stars have currents around them with enormous magnetic fields, because they're pulsars. And so as they start spiraling down, again, this is we're at a stage here. I'm going to go back here. We're at a stage around, for example, around 8 milliseconds. So they've gone. They're in the process of getting emerged, and you see. Remember, this side here is the mass. This is the magnetic field. Now, the magnetic field is just all twisted and wonky. Enormous magnetic fields going back and forth, back and forth, back and forth.
So is there a reason why the magnetic field side looks smaller than the mass side on the picture?
It's the region, the effect region that we're looking at versus density, right? Okay. In this particular case, it's the crookneck squash tail that's snapped off and recoiled, and it's being flung out into space. If you will, the recoil, the centrifugal force is flinging out material. So this here represents neutronium being flung out into space at relativistic speeds. It hasn't gotten as fast as the distortion of the magnetic field on this side. And so you watch this happening a little bit more. spinning around, the magnetic field gets to be, you start to see, but you do see tails of the result of the magnetic field. This material here, we're seeing the magnetic field effect is the neutrons being ejected and beginning to decay. Well, actually not beginning to decay, but colliding with stuff to create charge things where the magnetic field is getting messed up. Even though it's neutrons, it is affecting other material in the center, plus the original magnetic field of the neutron stars are being quite distorted. So this is another case of that recoil. You have magnetic recoil as well as material recoil going on. And so now as they get closer, the recoil gets more violent. The material is rushing out and being ejected quite a bit. And eventually, as it goes, it'll now you get the formation of a black hole. Other stuff starts going in, and you get really weird stuff. Three-dimensional structure is actually quite beautiful. We're sort of looking at the spot where the black hole is formed, and material has just been flung out quite a bit. And this happens. This is only like the first 16 milliseconds of this event. So it's very important. Why? Because this is going to be, we're going to talk about one of the, in the periodic table of elements, neutron star collisions turn out to be quite important. Yes, supernovae can occur. You can do some of the stuff. Lower mass stars can also form this stuff. But we've realized that neutron star collisions are actually much more common than we expect. How do we know that? Well, one of the things that's happening is that gravitational wave detectors like LIGO are beginning to sense neutron stars colliding. Apparently, neutron stars are much more common than we originally thought, and they're able to find each other, or they're formed in areas where they can be able to find each other and merge to form.
Or maybe a lot of them were binary stars, right? Before they became neutron stars.
That's a possibility. Also, globular clusters where there's lots of stars, they can sink toward the center and then find each other and then go and merge. Well, it's technically possible for neutron stars to form a neutron star. Usually, their mass is such that they'll form a black hole.
So what can happen? Can the same thing happen if a neutron star collides with a black hole, or maybe nothing?
Yes. Our first simulations took neutron stars to form a neutron star because when a black hole region forms, space gets really weird. You get a lot of divisions by zeros. It's a simulation nightmare. And in fact, for a long time, it was very difficult even to try to simulate neutron star black hole or black hole collisions. Now we've got numerical methods to try to simulate that stuff, but it's weird, right? This twisted magnetic space and magnetic field lines and space-time curvature. I mean, between these two objects, the space is, you're being pulled one or the other so violently that you don't know where up or down is, and the gravitational waves that come out of it are actually quite extraordinary.
Yeah, defining a grid to do your simulation on is problematic because the grid is warping. Yes,
it is, and you have to do very careful math. You have to be very careful because one of the things that the reason why they have the things have these being developed, the squash tail, is that these neutron stars, as they spiral down into each other, start to approach a significant percentage of the speed of light. And the neutron star is reacting to where it senses the other neutron star, not where it is. Relativity says that effects of gravitational effects travel at the speed of light. So one neutron star senses where the other one was from its reference, but it's actually at a different spot. It's sensing the other spot, and it ends up space-time gets to be so distorted that that nice grid of space you think in Euclidean, you can throw it out the window because it just becomes quite twisted and quite complex. We should probably move on to just dimension
Okay.
population 2 stars, and population 3 stars. Who wants to go on this one?
Here I mentioned that the different populations, like population 1 stars and population 2 stars, have a relatively high metallicity. But population 3 stars are have been born from pure hydrogen and helium, so they have 0 metallicity. And as you mentioned before, Tapio Weasel, that the metallicity is basically a term for anything heavier than helium, right?
Well, actually, or lithium, because
or lithium.
I mean, it is
Which is funny because lithium is a genuine, honest to God metal.
Yes.
Yeah.
Well, as I say, Feynman, told me that this notion of physicists calling everything, or astronomers calling everything above helium, lithium as a metal, is kind of a probably as a result of some astronomer being forced to take chemistry, not liking it, and just saying, they're all metals. They're all heavier stuff, right? It is not metal in the classical chemical sense.
Yeah, metal's like oxygen.
And so metallicity, really, you might say is non-primordial nuclei. But that's a mouthful. So his speculation, because I asked him why astronomers can call something like oxygen metal, is that, well, probably some astronomer who didn't like chemistry just said, it's an unfortunate name, but it's stuck.
Like we don't at least we don't see any nearby population 3 stars. So
no,
the only ones we could theoretically observe is from very far away. When we look back into the early universe,
Yes.
So it's probably the case that these population 3 stars were all very massive and they died long ago, basically. That's the idea of why there are no population 3 stars around us in our own galaxy, for example.
Yes.
Yeah.
And by the way, I mean no disrespect to chemistry. Chemistry is an important, enormous branch of science. On the case of the population 3 stars, these stars started off with basically effectively 3/4 hydrogen, 1/4 helium with traces of lithium. Their fusion process, for example, they start off fusing. They have nothing to do with C and O cycle, even if they're massive, right? Because there's no C in or O to do there. Their cores start off just turning hydrogen into helium. So their aging process is likely to be very different. Also, the population 3 stars probably occurred in much denser regions.
Yeah. Yes.
So they could become more massive. It's a speculation. So there's the speculation. There's a limit, Eddington limit, where beyond about 200, a normal star in a normal space around 250 solar masses gets to be so energetic, so brilliant, so violent that it tears itself apart, right? If you manage to get 500 solar masses in a normal spot packed together, the star would blow itself apart before it even really did much, right?
However, I have included that in the bottom right, that like very massive stars between 130 to 250 times the mass of the sun will produce photons energetic enough to undergo pair production. That you mentioned before, Tapio Weasel, about a star undergoing pair instability, and this is it.
Yeah. This happens because for gamma rays of sufficiently high enough energy, they can spontaneously turn into an electron-positron pair, which is nuts.
Yeah.
I mean, you have to have the photon has to be 2 times 511 kiloelectron electron volts.
Yep.
in depth, and they can, for them to create, that E equals mc squared, matter-antimatter, which then annihilates each other and does weird things. But the point is that very massive stars, whether they're population 3 or population 2 or population 1, are weird. They're not common out in the universe, but they are weird. And things like Eta Carina are just very unusual objects to study. There's a number of things about supermassive stars we don't quite understand. And I wish that Eta Carina would hurry up and go supernovae, because we'll learn a bunch of stuff from it. So come on, star, kick the bucket. Give us a nice...
And then would be called a hypernova, right? Like when a star like this.
And other weird stuff. And now, one of the things that Filippico's team is doing now that the acceleration universe is well established is they are looking at supernovae that are unusual, right? They only focused on the typical type 1a supernovae that were characteristic, but there are other supernovae that are unusual, and they're not paying attention because there's unusual physics going on there. I guess the other thing to say about population 3 stars is because they don't have much in the way of heavy elements, they have to generate their own, and the processes are might be slightly different in terms of how they do transitions. And this is one of the things that Webb hopefully can give us insight into what they're doing.
There's also one thing, two things I can also mention is that I've seen a PBS Spacetime episode that mentions that because in the early universe there was a lack of metals, which meant that the molecular clouds cooled slower due to the lack of metals. Yes. And that also means that the gas clouds did not fragment into smaller sizes. So that's why we had very massive stars, probably in the early universe. Very massive.
And so that era of reionization, or the cosmic dawn, as I like to call it, probably was punctuated by supermassive stars, well beyond the limits of normal massive stars of today, that went supernovae quite quickly and spread lots of material around, as well as enough to create black holes and neutron stars, and the neutron stars can collide and do other things like that. So it was a pretty chaotic time. The conditions of the universe were slightly different than they are now in terms of temperature and density. So some of those, we think that some of the population 3 stars could have become more massive and still stick around. The pair production supernovae that probably occurred even more frequently in the early universe still ionized radiation and still going on. By the way, those beeps are this is part of an experiment. We're monitoring radiation from the sun. The radiation is sun is putting out bursts of radiation, normal sunspot stuff. And we're getting cosmic showers as a result of particles reaching the Earth.
Cool.
Right, so those beeps are when the background radiation exceeds 0.4 microsieverts per hour.
So it says no one has observing the population 3 stars right currently, or
there are candidates
only by your own eyes.
There are candidates for population 3 stars, and the James Webb stuff is being studied, but this is something that we need sort of independent confirmation. So their population 3 stars are something that Webb is trying to detect, and we certainly have a couple of candidates, but not enough of a distribution to give us useful data. Yeah.
I've also seen that when you have a stellar mass of over 250 solar masses, it's the whole star could collapse into a black hole without even producing a supernova. And I've seen some, maybe they're very uncertain, but these are proposed to have been the seeds of supermassive black holes. Maybe we can go into that later.
That's debatable.
That's debatable. Yeah.
And the other thing about supermassive stars is, as they approach fusion, right? You've got a blob of material that's falling in from gravity. The speed at which you have hot material that collapses, and at some point you get some fusion going on. So you say there's a star starting while it's still collapsing, and you can get a massive enough blob that's pulling the material fast enough that whether it forms a star or not is kind of an academic debate. It'll just collapse to do other things. So, and also there's the possibility of primordial black holes doing stuff, but that's beyond the scope of this topic. So we should mention, however, galaxies. So massive stars, bunch of questions because they tend to be rare, but we hope to learn more. We should mention something about galaxies. One thing I should say is that you might remember when we talk about the Big Bang Flash and we looked at the cosmic background, we talked about harmonics of sound waves going through the early universe. And we mentioned at the time of the Big Bang Flash, 378,000 years after in the Big Bang process, that the primordial tone, the fundamental sound going through the universe, had a wavelength of around 500,000 light years across. These rings were about 500,000 light years across. Today, these rings are around 550 million light years across. And today, when we look at clusters of galaxies and their distribution, we find bubbles of clusters of galaxies whose bubble size is around 550 million light years across. That is, at the largest scale, the universe has sort of bubble shells of clusters of galaxies surrounding not much stuff in the center. Those 550 million light year across bubbles, on average, started at 500,000 light years across as sound waves in the early universe. Today, that note has been stretched by 1,100 times. And so the fundamental, wow, the sun's really putting out lots of bursts. The fundamental tone of the universe is B flat, but 71 octaves below the normal keyboard B flat. It's a very long way to fix it, but we do see the early shock waves in the early universe are responsible for formation of clusters called superclusters surrounding voids, not much stuff. The process by which galaxies form, and galaxies form into clusters, and clusters form into superclusters, is not fully understood. We have some models, and one of the things that the James Webb is supposed to help us with. So shall we go to the next one?
Okay.
I've seen like many simulations of like the early universe, and you see these like the supercluster tendrils forming in those simulations. Yeah.
Yes. So we're talking about an era of kind of 300 million years, 400 million years is when the galaxies began to form, we think. It's possible that the galaxies formed and then stars from the forming galaxies, or the way around. But the point is that galaxies form early in the universe. We think that galaxies might be a slightly later phase than star formation, but we're not sure.
Is there a possibility that the structure of some structure of galaxies could have been established before the first stars ignited?
Well, one of the things that we're hoping the Webb might show us is what we call dark galaxies, cold dark galaxies. That is, it'd be nice to see a very massive cloud of material in the process of collapsing to form potentially a core of a galaxy. If galaxies form first, then we should see gas clouds condensing, and out of that condensation, little pockets of stars form. The other possibility is that stars, particularly the more weird population 3 stars, go supernovae, and their shock waves collapse to form galaxies. It's also possible that they form stars. So it's to be determined. What we're seeing from the James Webb, and this was actually data they're talking to a person who uses the Webb about a week ago, is that there are lots of really small dwarf galaxies that are early on in the universe. And those galaxies undergo periods of star bursts and quiet. That is, they don't just get a galaxy and then lots of stars form. They go through periods where the stars appear to be, galaxies appear to be active and forming stars, to stars that will be where it goes back down into stars. That is, the galaxy comes into star formation, bursts, and then quiets down, and bursts and quiets down, bursts, quiets down. The thing we're seeing is
it oscillates. It
Yes.
oscillates between two states.
It's not just that it goes pedal to the middle and turns on, right? Well, certainly galaxies today don't form stars at the rate that they did before. It appears that galaxies undergo periods of bursts, sometimes because they're merging, but sometimes because of physics. So let's go to the next one.
Okay.
Back in the days, galaxies were seen as just clouds of stuff. It wasn't until people like Hubble that could actually see individual stars in the nearby galaxies, like Andromeda, that we realized that they're islands of stars. We really thought they were just cute little, they're called nebulae, right? Clouds of stuff. We now realize that there actually are piles of stars. And Hubble was classifying nebulae, these fuzzy blobs, and he has basically several types of classifications we see here. I guess the previous one, you skipped one, by the way.
Did?
Sorry to interrupt. I'm going to have to be going in a little bit.
Okay, we're very near the end.
Yeah.
So let's go to
Also,
galaxies.
next
one. Next one.
Okay.
Is the Milky Way. There certainly are galaxies that are active. Oftentimes because perhaps the massive black hole is going through a feeding frenzy.
Mm-hmm.
Next one.
But about a few slides ago, there was one image that showed that the population 2 stars are concentrated in globular clusters and in the center of the Milky Way, while population 1 stars are in the arms of galaxies of the Milky Way. So are globular clusters like remnants of mergers or something like that?
They may be the result of cores of galaxies that have been merged. Two kind of models of galaxy formation towards the end. One of them is a top-down, where basically a large gas cloud collapses and it forms a galaxy. There's things about that so the clumps interact gravitationally, and the the gas is not gravitationally stable, so it ends up forming a bulge in the center and spreads out as a disk. Whereas the other way around, the bottom up, is that galaxies form by merging. You get small galaxies that merge together to form big galaxies. So either gas clouds collapse to form galaxies, or small galaxies merge to form big galaxies.
Or you can have a combination of both, right? I think mergers are almost inevitable, at least sometimes. Like Andromeda will merge with our galaxy eventually, right?
Yes.
So
and big galaxies like the Milky Way absorb small galaxies. In fact, we detected a number of small galaxies, dwarf galaxies, that have merged with the Milky Way and in mapping our galaxy. The galaxy formation model, let's go flip the next one.
Okay.
And this is the bottom up where galaxies merge to form big galaxies, as opposed to gas collapsing to form small galaxies. So next one.
Okay.
There are certainly, one of the things is that what stops the process of contraction, right? Why would a big gas cloud just collapse and form a giant massive black hole? Well, they actually might, but perhaps radiation pressure from stars forming keeps it from collapsing too fast. Perhaps the black hole active nuclei pushes stuff out. Perhaps the dark matter, whatever that is, the excess gravity on the outside pulls it out. But the theories of current galaxy formation are not successful in predicting this rotation speed and size of galaxies, right? When we look at the theoretical models, they don't match reality. So we know we're in trouble. The sort of Landau-Cedium model needs refinement because it underestimates the number of thin galaxies in the universe. They predict a large number of mergers, more than we see. And if mergers are stuff, the problem is the mergers sometimes destroy the galaxies. Sometimes the result is the galaxy is not a nice thin spiral, but an elliptical blob. And we don't see that with the distribution.
But do like elliptical galaxies eventually become spiral galaxies over time still, or do they remain?
The tendency for that to happen. So if we just I guess this is just some graphs talking about the mergers. This next one, whether deaths of stars collapse or other material collapses to form more massive black holes is a question. Open question. Next slide. Again,
I found some papers discussing the role of supermassive black holes, like whether we have primordial black holes or whether we have direct collapse black holes, or something like that. Yeah, this is a very uncertain area in the more recent history of the universe.
And partially because we were able to detect earlier galaxies that are formed earlier in the universe. And also have these giant surveys to begin to collect lots of data. So going back on redshift, going up in that graph is farther back. Next one is essentially again the notion of how things like the Webb or a new thing called LISA, which would be a gravitational wave detector in space, might help us understand black hole formation and mergers and galactic formation.
Like primordial black holes, were those the seeds of supermassive black holes? There's an open question.
Were the seeds of galaxies? Did they help cause star formation? We don't know.
Yeah.
And
but there is an interesting relationship between supermassive black holes and galaxies. Like there's a linear relationship between the supermassive black hole, the mass of the supermassive black hole, and also the mass of the galaxy as a whole.
So near the end of there, one more thing. The Webb shows that early galaxies, might have been more spheroid, or they might have been,
and they were all small, right? Smaller as well. Yeah.
They tend to be dwarf, but we're seeing bigger and bigger. We're seeing more developed spirals early on in the universe that kind of puzzle us. So finally, we're going to end this show talking about the era of dark energy. Up until the now of 9.8 billion years in the process, what's dominating is gravity, right? And if we go to the next spot here, we talk about the fact that we're entering into a dark energy era where gravity is no longer the dominant force. Dark energy is. The universe is accelerating, and weird things happen. We're not quite sure, but we know that around 4 to 5 billion years ago, the universe turned a corner. The rate of expansion was kind of slowing down, but now dark energy is taking over and has overcome gravity when to slow stuff down and is accelerating it back up.
Yeah, you can see in the image on the left, you can see the log scale of the age of the universe and a log scale of the size of the universe, and you can see that it's linear. Like for every 10 to the power of 1 log age, you have 10 to the power of 0.5 on about that increase in size. But eventually, as you hit the dark energy era, when dark energy becomes the dominate, then the curve shoots upwards. The universe begins to accelerate the expansion rate.
But we have to be careful, however, because we don't understand dark energy. We just see its an effect. We don't know if dark energy will continue to do what it does, or it will perhaps even reverse. We don't know. If you don't know what dark energy is, you can't say it will expand forever, accelerate forever. It looks like it now, but that's because we really don't understand what dark energy is, other than its effect. Its existence is well established by multiple observations. The fate of the universe and what it'll do, which is not part of BE, is unknown. So, sorry for the length of time. Stars typically spend billions of years doing what we did in a matter of a couple hours.
Right, real fast. Anybody has any questions in chat, ask them now or forever hold your peace.
Yeah.
And before you have to go, if you have to go right now, Tapioca, you have anything you want to advertise?
I will be appearing tomorrow on Bad Science Sunday. I did a relevant show on Skeptic Haven this past Thursday, which people might find interesting. We talked a lot about dark matter.
Yes, and the was it were you on the it's mass or it's modified gravity things?
I personally think it's more likely to be mass, but I think it's an open question still. It definitely you can map it, and to me, that intuitively, that seems more like a property of something that would but it could be a field.
I suspect that like the controversy between mass and mond would also apply to the early formation of galaxies, perhaps also.
Well,
dark matter is just one version of modified gravity. I'm not a big fan of mond, but there might be other vector tensor versions of gravity apparently are.
Do these different models predict differences in like galaxy formation, or
they tend to run into problems of reality?
And they tend and CMB,
as they fail.
None of them explain the CMB. Well, the main criticism people have against a particle theory of dark matter is that we haven't found the particle yet, which I just don't think is a very good argument against it.
Yeah,
we have our first question.
Yes.
I don't know about that. Science is very good about holding on to old names that aren't very good. So,
what was the question?
Oh, it's the question is, do you think dark energy will get renamed when it gets better understood?
Given the history of astronomy, if we call planetary nebula to this day, I doubt that dark matter would be the stuff. It's always important to say what dark matter is excess gravitational fields caused by what?
Yes.
Excess of what? Excess of what current gravitational models would predict. Right? Our current understanding of gravity, we have on average about 6 times more gravitational interactions than we can account for with mass.
Mhm.
Why? Either because there's mass that we haven't detected, so-called dark mass, or because the equations of gravitational things are not correct, or a combination of both, or something else. We don't know.
If we learn more about early galaxy formation, perhaps it would also give us more information to come up with an accurate model of gravity, perhaps. Right?
I think the early galaxy formation will help confuse us more.
Yeah.
And I think it will help us toss out even more models. The dark matter, or the excess gravitational fields, are very important in galaxy formations and galaxy cluster formations and galaxy supercluster formations. And if you want your simulation to produce a universe that's vaguely like today, starting early on, you need to add both the effects of dark matter, excess fields, and normal matter. Right? If you do one and not the other, you get a universe that doesn't look like anything today. So they're both important. What it is, who knows? Good question, though.
Well, you, Len, anything coming up that you want to advertise?
Yes, on the April 27th at 16:30 Pacific time, we have a unnamed tavern, which is not a tavern, mini show, and that's on April 27th on Chesh's channel, also on Chesh's channel and in their debate hub. On May 3rd at 1 p.m. Pacific time is a volcano show, where we're going to update on what the Kilo volcano is doing and a little other volcano stuff.
Oh, there is actually 2 more questions in the live chat. I don't know if you want to answer these.
Sure.
Oh, like Al Tucker asks, does Mont really have or hold any water? That's one question.
It's too much to get into.
I know. I think the answer is that at one point it looked quite hopeful, but one of the problems that some Mons run into is binary stars, pairs of stars that are far apart, so-called wide binaries. They're not behaving like Mond or some Mons do. You have to be careful, because some people, you can cook a theory and match the curve and say, look, I'm right, and be wrong, right?
It's very, it's a lot.
Now the part of the problem that particle physics has is that the standard model of physics is very successful with stuff we know about.
Mm-hmm.
But
too successful.
It one does not account for the gravitational effect. Although gravity may not be a quantum thing, so that may be okay. 2, it doesn't account for. It doesn't show obviously what a dark matter particle might be. And 3, it has nothing to say about dark energy, which is about 69% of the universe. So the standard model accounts for about 4% of the universe, and does very well. And I'm not disrespecting it. It's just that it would sure be nice if they found in CERN or if one of these other detectors underground that are looking for dark matter particles. It'd be really nice if they say, see, there's dark matter stuff. But the problem is the mass that you might say is a dark matter particle has to be stealth, right? Astronomers have never seen dark mass that absorbs light, reflects light, or transmits light.
Yep.
It says that mass has no temperature, is not glowing any black body radiation, and astronomers are very good at finding very subtle, faint sources of light or dips in light curves. We've never seen so-called dark matter mass do anything to light on any frequency, from gamma waves to radio waves. It appears to be completely stealth.
We haven't seen it do anything non-gravitational.
Yes.
Does it get absorbed by black holes? I don't know.
No, black holes. I mean, black holes. Things that come out of black holes are 1, the gravitational effect, 2, charge, 3, spin, and 4, Hawking radiation. But from the point of view of gravitational mass, right? There's not enough black holes to count for dark matter, so-called.
I'm not saying that black holes is dark matter. I was just wondering whether dark matter can get absorbed by.
I'm
black
sorry,
holes.
I'm getting a phone call, so I actually do have to go.
Sorry.
Yeah.
We'll
as I say, your
we'll
question.
talk to you about the next meeting
Yep.
in chat later.
Will do. See you guys.
Are you saying before?
Like I was maybe wondering whether black holes are able to absorb dark matter like it can absorb normal matter.
Well, if dark matter is stuff can fall into, go beyond the event horizon of a black hole. If dark matter is a result of gravitational fields being different than the normal inverse square stuff and general relativity, then no. So if dark matter is stuff can go into a black hole event horizon. If dark matter is a misunderstanding of gravitational effect, then the answer is no. It's different.
That could perhaps form a hypothesis to if we are able, we can observe black holes very closely, and perhaps we can see it increased in mass, but there is
fortunately we can't observe black holes closely.
Right,
so,
right. Exactly. Unfortunately,
yeah. So we have a BE4, the final show, which is coming on the May 18th. Is right?
Yes. I will talk about this 1 second. All right. Coming up on my channel real fast. In 1 week, me and my friends will be reviewing the Saw movie series. So if you have a weak stomach like I do, don't watch that episode. In 2 weeks, we'll be me and my new friend will be reviewing the Ornithian dinosaurs / bird-hip dinosaurs and their fun family tree. And in 4 weeks, we will be having the grand finale of the Before Earth series, our solar system to the Earth. Earth is here, and that's our finale. So,
Landon says he lost connection. He's back.
Okay, back in.
Big finale of when the Earth finally gets here, in 4 weeks from now.
Yeah. So B4, we're going to cover a little bit more about supernovae effects and neutron star measure effects and gas clouds forming. We're going to talk about now 4, and we'll talk about the formation of our solar system, and finally what happened to formations of planets and what happened to Earth Moon, ending with about the Earth
The connection is really bad.
8 million years old.
Yeah, you're a little robotic right now, but we'll.
Yeah, I think the connection is really bad. Sorry.
Well,
Yeah,
anyways, we'll talk about that.
The connection comes
And we'll talk about all this in chat, but hope you all have a good time. Never stop learning. Enjoy the randomness. We'll see you next week. Bye.
Bye.